So today we're going to talk about radiative transfer with partial frequency redistribution. This is a bit of an even more technical subject than we already have dealt with here. But this is an essential ingredient of line formation of strong chromospheric lines like the calcium H and K line, the magnesium 2 H and K lines, Lyman alpha, Lyman beta. So I will go a little bit over the theory. I will go a little bit over how you incorporate this in a radiative transfer formalism for multi-level accelerated lambda iteration. And I will show a couple of examples of cases where the PID is important and even where it is important for the physics of the atmosphere. So I'll start with showing you what PID is, how we incorporate it in a MALI method, multi-level accelerated lambda iteration. That's what MALI stands for. I'll show that it doesn't really affect very much the convergence properties of the code, which is good. And actually, I will skip the computational speed up through multi-threading. That's not so important here. So then I will give you some examples. I will show you that the cooling in the calcium K line is in fact dependent on, depends to a degree on whether you assume complete redistribution or partial frequency redistribution. Calcium K is one of the most important radiative coolers in the solar chromosphere. So anything above the temperature minimum gets heated by mechanical processes, wave dissipation, magnetic field dissipation, but gets cooled to balance that heating. It gets cooled by radiative losses in the calcium H and K lines and also the magnesium H and K lines. Then we'll talk a little bit about how partial redistribution in the Lyman alpha line affects the ionization of hydrogen. This is a kind of maybe a bit counterintuitive, but the line formation of Lyman alpha affects the population numbers in the lower level of the H alpha line, which is also the lower level of the Balmer continuum. And the Balmer continuum is the mechanism through which ionized hydrogen ionizes radiatively. And so therefore the physics of the formation of Lyman alpha is important for hydrogen ionization, as I'll show you, hope to illustrate for you. And then we'll talk about an interesting formation of the oxygen 1 triplet. The oxygen 1 triplet is 3 lines at 130 nanometers. I've shown them to you before when we talked about absorption and emission lines in the first talk that I gave last week. And the interesting thing is that these lines share a common upper level. So they have one upper level and 3 separate lower levels. And when you have this situation, you can have, as we'll see, partial redistribution has to do with coherence of scattering, where you conserve the wavelength of the incoming and outgoing photon. When you have a situation where 3 lines couple through a common upper level, you can have coherent scattering when you absorb in one line and then coherently scatter in another line. And this is an important effect for these to model these lines properly. And then I'll have some conclusions at the end. So just to give you an idea of the importance of partial frequency redistribution for the formation of these strong lines, I'm comparing here, this is a plot of the magnesium, not the calcium, H line, calculated through a Val model, probably Val C, at 2 different viewing angles. One is close to this center and one is closer to the limb. And you see this is the line profile computed in CRD. And then I overplot here the line profile calculated with partial frequency redistribution. And you see that there is not much difference in the line wings, even though at the limb, closer to the limb, there still is at these wavelengths, there is still difference between the 2 approximations. But in the line core, you can see that the difference is very big, both in shape and in intensities. So this already makes clear that indeed partial redistribution is a relevant and important effect. If we were to interpret, say we wanted to do an inversion and we wanted to invert the calcium H line or K line, and we would use CRD as an approximation, we would get very different properties from the atmosphere than if we would do the same analysis using PRD, the proper formalism. This is an observation of the magnesium H and K lines, not by IRIS, by the way. This is a spectrum that was taken with the SMM satellite that flew in the 70s. That has an interesting history. It was the first satellite, I think, that was repaired by a space shuttle crew. They were able to go to the satellite. It had a problem with, I think, a mechanism that was stuck. And they docked with the satellite, grabbed it, fixed the problem, and released it. And after years of not being operational, it did some very nice observations, both in these lines, even with polarimetry. There was polarimetry of the magnesium H and K line. It was a single pixel detector, so it took a long time for them to take spectra because you had to go wavelength by wavelength through the line, and then polarization step, modulation by modulation. So it took a long time, but the spectra are very nice, as you can see. So these are, by comparison, the magnesium H and K line profiles calculated with CRD, both in black close to this center, as the observation was, and in yellow closer to the limb at μ=1, I believe. And you can see that there's no comparison. I mean, it's clear that CRD is not the right way to calculate the line profiles of these lines. And here is the CRD profiles for the two angles, the PRD profiles, and you see that there's some intensity differences, which probably has to do with the thermal structure of Val C not being exactly what it should be. But you see that the shape of the observed line profile is extremely well reproduced, especially the narrow K2 reversals, the K1 and H1, the K1 and H1 minima, and maybe less so the peaks, but they are very sensitive to the chromospheric temperature structure, which you don't necessarily reproduce very well with a one-dimensional hydrostatic model. So, in summary, it is very clear that PRD for these lines is an essential ingredient. And then finally, these are the hydrogen Lyman alpha line profiles calculated in CRD for 3 different viewing angles, where mu is the cosine theta of the angle at which you look at the atmosphere. And you see that if I overplot the PRD line profiles, that in CRD, this is a logarithmic, note this is a logarithmic plot, that these line profiles are much, much broader in CRD than calculated with PRD. So again, Lyman alpha line formation is very different, whether you assume complete frequency redistribution or partial frequency redistribution, even though we don't know yet exactly what that means. But it's clear that it is necessary to explore that mechanism. So what is partial frequency redistribution? Imagine that you have a spectral line, you have radiative excitation, de-excitation. This upper level lives in the excited state for a finite time. Typically for very strong lines, this is 10⁻⁸ seconds. So 10 nanoseconds, right? Very short period. But during this time, it is possible that that other particles come close to this atom and perturb its energy states. They change the phase of the wave functions a little bit. They maybe change the energy level a little bit. And if that's the case, you can imagine this upper level as some kind of continuum of sublevels, where the width of the energy range is about the width of the energy difference that makes the width of the line, if you understand what I mean. So that energy difference relates directly to the width of the line in wavelength. Now, if there are the lifetime is relatively long compared to the collisional frequency, the incoming and outgoing photon will be uncorrelated. They will be close in wavelength, but not necessarily exactly coherent, and there will be phase differences. So these photons, incoming and outgoing photons, are considered incoherent. And in that case, we have what we call complete frequency redistribution. If all atoms statistically suffer this kind of a perturbation, then the line forms under complete frequency redistribution. And this is the case for most lines, apart from the handful of lines that really suffer from PRD, mostly the ones that I've shown you already. Now, if the collisional rate, when you go up higher in the atmosphere, reduces because the density falls off with height, and the lifetime of the excited level becomes short compared to the collisional frequency, right? Then some of these scatterings that occur in this line are coherent because during the lifetime of the upper level, the atom is not perturbed, and in that case, the incoming and outgoing photon will be correlated. They will be exactly, so they will come into some sublevels, some of these sublevels, and the atom not being perturbed, they will leave exactly from that sublevel. The atom will not be reshuffled. And so these photons have a correlation in wavelength or frequency, if you will. And we have to account for that because it changes the absorption profile, as we will see. Now, to describe that, we people back then, already starting in the 60s, David Hummer, by the way, lived here in Boulder, right? And he was actually one of the co-founders of the first microbrewery here, I believe. So that's a nice side story. But so they define this laboratory frame redistribution function. Well, what you do is you first define it in the atomic frame, and then you see how it transforms into the observing frame when you have Doppler velocities present and you have a velocity distribution. But we will talk only here about the redistribution function in the observer's frame. And so this redistribution function as a function of frequency and direction of the incoming and outgoing photon over a frequency band and over the incoming and outgoing solid angles describes the conditional probability that when a photon in the line ij and in solid angle d omega prime around direction n prime and frequency range between nu prime and nu prime plus delta nu prime is scattered by that line, it will be emitted into an angle d omega around frequency direction nu and frequency range nu and nu plus d nu. So I had the prime and the normal ones in reversed. So in this case, the incoming photon is the prime and the outgoing photon is the unprime. So this is just a definition. This describes this distribution, that the probability of an incoming and outgoing photon, how they are related in frequency and direction. So when we have, complete frequency redistribution, this redistribution function R is just the product of the absorption profile at the absorption frequency times the absorption profile at the emission frequency. The photons are uncorrelated. Right? And remember that this is the conditional probability, that when you have a scattering, this is the probability of a photon having frequencies nu and nu prime for the incoming and outgoing photon. Yeah. Again, so this is a definition and how you derive that redistribution function. We're not going to touch upon here. But it's easy to see that it has certain properties because this is a conditional probabilities integrated over all absorption and all emission frequencies. It should be equal to 1. And if I integrate over all absorption frequencies, then I should just get the absorption profile. Now, I told you about this transition and the upper level being perturbed. You can imagine that that doesn't happen 100% of the time or 0% of the time. There's a fraction of atom that get perturbed depending on the relative rates of collisions and the rate of de-excitation by spontaneous emission, right? And so typically this redistribution function is a sum, just a geometric sum of a complete redistribution in the observer's frame and coherent scattering in the observer's frame. And this coherency fraction gamma is the ratio of the total rate out of the level plus the total rate plus the collisional perturbations that happen. And you can so when the rate out of the level, mostly because of stimulated emission, is very high, then the atom, so at least the lifetime of the excited level is very short. You can imagine that there's no time for the atom to be perturbed. So the coherency fraction will be very large. If the collisional frequency, this QE, is very high, you can see that the coherency fraction typically will be close to 0, right? Because during the lifetime is so long of the excited level that there will be always a collision perturbing the atom and there will be complete redistribution. Is clear so far? Any questions? Yeah.
Sorry if I followed actually correctly. So about this gamma factor, so PK is
the total rate out of level, the upper level.
Okay. So meaning radiative collision.
Radiative collisional, yes.
Everything. Okay. And then Q only counts for the collisions.
QE is the elastic collisions.
Elastic.
So not the so PJ contains the collisional de-excitation. Yeah, if you just consider the line between I and J, of course, there are rates that go to other levels as well that you have to account for in PJ, because they determine the lifetime of the upper level. So this is not the collisional. This is not related to the collisional excitation or de-excitation. It's more related to the van der Waals broadening or Stark broadening. All of those contribute to these elastic collisions. And that's how you calculate it in the code. Now, after some algebra, which if you're interested, you can I'll give you some of the references at the end, or you can go back to the earlier references, the Hammer and Heinzel and Hubeny paper. You can show that the emission profile in PRD is given by this expression, and we'll go through it first. So if we have complete redistribution, I showed you that this redistribution function is given by the product of phi at the absorption times the phi at the emission frequency, right? So in that case, this is 0, and so in that case, the PRD or the emission profile is just the absorption profile. Right? Also, if the coherency fraction gamma is small, we also have a profile that is very close to the absorption profile. Right? If the radiative rate is, or if the rate out of J is relatively large, then well, then actually these cancel, so that doesn't matter directly. Right? But you can see that this is actually the expression for angle average redistribution, because you see we already integrated over angle here and assume that the redistribution function does not depend on angle, or you can separately integrate the angle dependence of the redistribution function and that of the radiation field. A little bit later, we'll talk about angle dependent redistribution. And in that case, the angle integration between R and J is coupled. And this is the case when you have large velocity gradients in the atmosphere, then you cannot decouple these angle integrations. So this is just to give you kind of a feeling of what this PRD emission profile entails. In the case of complete redistribution, where the coherency being very low, the PRD emission profile will just be equal to the absorption profile. And this is what happens deep in the atmosphere, because deep in the atmosphere, QE will always be much larger than PJ, and this coherency fraction will be 0 or close to 0. This is a typical shape of the redistribution function R divided by the absorption profile. So this is this expression here in yellow is plotted here for different absorption frequencies, and you can see that. So this basically tells you that there's in the line core there is a little bit of complete redistribution. This distribution here, for instance, at 1.5 is flat. So this is this is the these are the curves for this expression for different emission frequencies as shown here by X, the Doppler with normalized frequency. So these are Doppler units. But you can see that if a line absorbs a photon, for instance, at X prime equal 10, it mostly has a larger probability of being emitted at the same frequency, right? So this is the essence of coherent scattering with some probability width to that probability. So this is what the redistribution function tells you. And then in the line core, you have a little bit of a broader distribution. So you absorb any of these photons, there you have a probability that is very close to for different emission frequencies, actually, if you would plot those as well. This is, by comparison, is the void function at X prime equals 0. So in the line core, you basically have this redistribution is very close to the CRD absorption profile. So, like I said, we have complete redistribution in the core because the red and the black line here, our curves are very close to each other. We have coherent scattering in the wings, and we have a decoupling of the wing source function from the line core source function. Because once you are a photon in the line core, then you have some probability of going to other wave frequencies. But mostly you stay in the line core. And once you're a photon in the line wing, you stay in the line wing. While in complete redistribution, if you are absorbed in the line core, you have a significant probability of being emitted in the line wings. And this really changes the dynamics of radiative transfer in a strong line like this. So I will leave this for you to go through once after the talk or whenever you have time. These are some interesting papers. You may note that these are all from the early to mid 70s. So we've known how to solve these problems already for a long time, except we have much faster computers. We have better numerical methods multi-level solutions. But in principle, all these effects were well known back then. So progress sometimes is slow. So how do we incorporate this partial frequency redistribution in the numerical method for solving radiative transfer in an atom that has many levels? And I told you MALI stands for multi-level accelerated lambda iteration, where accelerated lambda iteration is the mechanism that we talked about yesterday to solve the transfer equation when you have significant contributions from scattering. So the method is based on 2 papers by Rybicki and Hummer, and this is where the name RH comes from, by the way. The code is named after this method, which is the essential method to include in the code to solve non-LTE radiative transfer. So RH stands for Rybicki-Hummer. The method that you can design employs preconditioning. Preconditioning is a term where when you have nonlinearities and I told you the equation of statistical equilibrium for the population numbers is a strongly nonlinear, non-local equation. You can incorporate preconditioning where for some quantities, if you don't want to deal with these nonlinearities, typically when you have a nonlinear differential equation that you want to solve, you can introduce perturbations and write the linearization and solve for the linear component only, right? That's kind of a typical approach. The nonlinearities that are involved with radiative transfer, and in particular when you look at how the PRD affects the nonlinearity of the transfer equation. You can imagine when you have this emission profile that depends on I, and I depends on the population number. So you get very nasty nonlinearities. It's not good to try to write down the complete linearization of that equation. It's much easier, turns out, in some steps to take the values of these quantities from a previous iteration. And that is what preconditioning tells. So you take away the nonlinearities by replacing some of the properties in your equation by the values from a previous iteration. And so your convergence might be a little bit slower, but it's much easier to understand and it's much more straightforward. And you can solve it. That's the big thing. Right? So that's what's described here. And then at the RH, the Rybicki-Hummer method explicitly allows for cross terms that are the result of overlapping. So it corrects the radiative transfer from one step to the other in the iterative process for this overlap of radiative transition, and that's an important property of the method as well. So you correctly deal with that in the iteration process. And like the Axel, well, that's where the name comes from. We employ a local operator, and you have different choices. So you can, when you do this operator splitting, the simplest choice, as I showed you yesterday, is to employ a local operator, a diagonal operator that you can analytically bring to the other side of the equation. There are different options. You can do it differently, but the idea was that this method also should be very useful in higher dimensions. And then if you have a non-local operator, things become very complicated because then you depend not only on different points in space in depth, but also on different points in horizontal direction. And so having a local operator again might slow you down a little bit in the convergence process, but it's much easier to deal with. And the code employs NG acceleration. I don't think I have any slides on that. Does anyone know what that is, by the way? Has anyone heard of this acceleration? Yeah. So NG acceleration is one example of a suite of methods, like a class of methods that use a mathematical approach to, if you have a series of solutions, so you do an iterative process, you have one solution, then the next solution, then the next solution. It is a mathematical method to optimize the next iteration step so that it's closer to reality than what you would get if you would just follow the iterative process. So it is a purely mathematical minimization of the next iteration step, given you have a number of prior iterations. And it actually greatly can increase the convergence rate of a code. It also, you have to be careful with it, because if you, this mathematical method knows nothing of the physics of the process that you're looking at. So it may give you, if you turn it on too early in the process, when the nonlinearities are still large, it may give you a solution that has negative population numbers, for instance, because it doesn't know anything about that. And of course, then terms like e to the minus tau blow up when tau is proportional to these population numbers, and you get a big thing that explodes. So that says a bit careful. So when we write down now, very much like we did for the two-level atom that I showed you yesterday, we can write all the expressions for the bound and bound-free transition probabilities in terms of the Einstein coefficient and the population numbers, and the absorption and emission profiles. Now note that in this case now we have PRD. So these were in the two-level atom that we talked about yesterday. The phi here and here was the same. We now have an emission profile that depends on the radiation field, partial frequency redistribution. And this is a stimulated emission term, right? Which is just treated as a negative intensity, negative absorption, sorry. And so this is the spontaneous emission, and again, it has the PRD emission profile. Similarly, like yesterday, we can write the radiative rates, absorption and emission, or excitation, de-excitation, by doing the proper integrals over wavelength and solid angle. It's exactly the same as we talked about yesterday, except we have a more general expressions for the lines and the continua that we are dealing with. And we can, this is exactly the same expression now, the equation of statistical equilibrium for the population number. So this is the, in our formulation of the multi-level accelerated lambda iteration, this is the prime equation that we want to solve. And basically the radiative transfer equation is the additional equation that you have to satisfy to make the solution proper, right? Consistent. So we have the collision rates, the radiative rates. And now we can, just like we did yesterday in the two-level atom approximation, we can have a approximate formal solution. We introduce operator splitting, where this psi operator is now uppercase psi, not to be confused with the PRD emission profile, operating not on the source function, as we did yesterday for the two-level approximation, but on the emission coefficient. And this is a little bit easier to understand in terms of linearization when you have PRD. And then we introduced this approximate operator, psi star. And in this case, this part, the difference between psi star and the realistic psi, we write it as operating on the preconditioned value of the emission coefficient, the iteration from the value from a previous iteration. And this takes out, so this term is now all known because it comes from the previous iteration. And this makes solving this relatively easy task, right? And then we introduce a function rho, which is the ratio of the PRD emission profile over the absorption profile. And it turns out if you all implement this, so rho given by what I showed you earlier for the shape of the PRD emission profile is given by this expression here. And then so to extend the CRD Mali formalism that was published by Rybik and Hummer, to extend that to PRD, we need to calculate the redistribution function so that we can evaluate this integral. We need to evaluate this ratio rho by making this integral, doing this integral, this you can imagine that this changes the redistribution of the emission profile, but we can iterate this in a separate loop where we keep the population numbers fixed, and this is very fast. Naively, when you look at it, it might look like lambda iteration because you have a source function, you calculate the radiative transfer solution, and you plug that back into your source function, etc. But since you keep the population numbers fixed, you don't generate any photons, which is different from regular lambda iteration. So naively, at first, you might think that this would converge very slowly, like we have seen regular lambda iteration does, but this actually converges typically very fast. You have to do like 2 or 3 iterations for the radiation field to become consistent with the redistribution function. And then you have to correct the line profile with this factor rho. This when you look at the radiative transfer code, so there's some additional mechanisms here that add to the code. But when you look at the Mali iteration scheme, this adds literally 1 line to the code. It's quite shocking when you see how complicated partial redistribution is. But this mechanism, apart from the fact that you have to iterate in a separate loop, but the radiative transfer solution is just solving the equation of radiative transfer with this rho applied to the absorption profile. So it's not that complicated technically. And it converges very fast. This is a PRD solution of hydrogen in a one-dimensional atmosphere. These are the number of iteration steps to reach a relative change in the maximum relative change in the population numbers to 10 to the minus 10, and it takes about 50 iterations. This compares CRD and PRD, so you see that the CRD converges a little bit faster, but not that much faster. It's very similar, comparable. Magnesium is a little bit more difficult, just because of how the rates are sensitive to properties in the atmosphere, and calcium actually in this particular atmosphere converges faster in PRD than in CRD, which is interesting. I don't know exactly what the reason for that is. It may be that actually because you do these additional iterations to get the rho consistent with the radiation field, that some of the scattering that you apply that is relevant for the line formation is already solved by these iterations, and that's why the PRD goes faster than the CRD. So now let's talk about some practical implications of PRD. And how are we doing with time, by the way? I'm talking a little bit long, I think. 10 minutes? Okay. I may carry over like 10 minutes of this talk to, but I think the RH is a little bit short. So this is now, you've seen a similar plot before when we talked about the particular line formation and how the intensity in the calcium H and K lines depends on the source functions, the shape of the source function. This is now a plot of the situation with the Planck function and the source function at the Balmer continuum. So the Balmer continuum is the bound free transition from the first excited level of hydrogen the upper level of Lyman alpha, the lower level of H alpha, to ionization. Now, it turns out that most of the ionization by radiation in hydrogen in the solar atmosphere is by ionization from the Balmer continuum, not from the ground level. And the reason for that is that there are many more photons in the Balmer continuum than there are at very short wavelengths like the Lyman alpha continuum at 90 nanometers, right? So most ionization in hydrogen by radiation is from the Balmer continuum. This implies that the radiative transfer in Lyman alpha is very important for hydrogen ionization, because what happens in Lyman alpha determines the number of atoms that you have in the first excited state of the Balmer, or and that therefore the lower level of the Balmer continuum, right? In addition, the optical depth of the Balmer continuum is such that the radiation field at this wavelength, which is 384 nanometers, already decouples deep in the atmosphere. And so the radiation field is mostly constant. This is J here in this greenish yellow. And this accentuates the effect of the importance of the population number in this N2 level, because this radiation field is constant. So whatever the atoms offer in terms of number of populations in this N2 level, the ionization will happen, right? And so the ionization rate really depends on how you populate this N2 level, not so much what happens in the continuum itself. Is that clear? Okay. Now, how does this affect, how does Lyman alpha, PRD in Lyman alpha affect this ionization? This is the, again, this is the same plot I showed before. This is the comparison between the line profiles of Lyman alpha calculated at different heliocentric angles through a one-dimensional hydrostatic model, I think FALC probably. And one thing to notice is the very big difference between the width of the line and the broadening of, or the broadness of the Lyman alpha wings. Now, what you can imagine is that you remember the temperature profile of the atmosphere, and maybe I can it shows here. Yeah, you can. It shows a little bit here. So you have the photosphere, temperature minimum, chromosphere, and then a very steep temperature increase here, which is the transition region. The transition region is there because at the top of the atmosphere, the chromosphere is cooled by radiative losses in Lyman alpha. Once temperature increases, neutral hydrogen gets more and more ionized. And once you completely ionize hydrogen, there's no more cooling by Lyman alpha. So it's a runaway effect. You reduce the Lyman alpha cooling, therefore the temperature gets higher, and that's why you have a transition region that is so steep. But when you have this, just before all hydrogen gets ionized, you have these high temperatures, and some of the radiation doesn't escape upward, but also goes down. And when you have these very broad wings in Lyman alpha, the broader the wings, the more photons go down. And when photons go down, there is a hot radiation that excites Lyman alpha at lower levels. And when you excite Lyman alpha at lower levels, you ionize more in the Balmer continuum. So that is the mechanism. So when you compare CRD to PRD, there's much less, in the case of PRD, there's much less radiation that is returned to the lower layers of the atmosphere, and that excites Lyman alpha, and therefore this effect of PRD reduces the ionization of hydrogen. So it's a kind of a very how do you call it, spect process, indirect, but there's a significant dependence of that. So to calculate hydrogen ionization properly, you do have to include radiation in Lyman alpha and Lyman beta to a lesser degree in PRD. Otherwise, you overestimate the ionization of hydrogen in lower layers. And you can see that effect. This is now a plot of the departure coefficients. The departure coefficients is the ratio of the non-LTE population numbers over the values that you would get if you would assume LTE. And the curve here to look at is this the curve for H2, which is the ionized hydrogen, right? Just protons, of course. And so this positive value of the departure coefficient is the result of this back radiation in Lyman alpha. So that causes an excitation in Lyman alpha that is higher than it would be in LTE. And this excitation is higher in CRD when you assume CRD in Lyman alpha than when you assume PRD in Lyman alpha. So this difference here makes a difference for the ionization. So now let's go to, I think this is probably the last topic I do before the break, and then I can do one more, the oxygen afterwards. So this is a time series of spectra. So this is wavelength, this is time of the calcium K line from a one-dimensional simulation. The Carlson and Stein one-dimensional hydrodynamic code, Radin. And you see, this is the shape of these spectra is evidence of shock waves passing through the atmosphere. So what happens is a shock wave passes through optical depth unity of the line core and causes this brightening and blue shift because the shock wave moves up and it has a temperature spike. And then after the shock passes, the line core becomes cooler or senses a cooler region, and a redshift because the material falls back after the shock. And these are called K2V bright point because they specifically brighten the violet K2 peak. And the balance of this heating, so this locally heats the atmosphere. The balance of this heating is radiative cooling in the calcium H and K lines. And so now we will investigate a little bit how PRD affects this radiative cooling, and it actually turns out that it does. Again, we have the in this case, because we have strong velocity gradients, we cannot decouple the angular integration of the redistribution function and the intensity. So we have to solve this integral explicitly, which takes significantly more computational time to do. And this is just a few plots of the redistribution function. You see that the shapes are somewhat different. So these are for different angles. Mu of the outgoing and incoming photon, and different frequencies, like I showed you before, is not so important, these details. This again is the difference between CRD, dashed line here, and PRD, and the line profile calculated when you explicitly solve for this angle dependence, in this case in an atmosphere without velocities. So you would expect that they should be very close, except that in the case of regular PRD, which is angle average PRD, you decouple the angular integration of the radiation of the redistribution function and the intensity. So what we want to evaluate is the cooling rate that is the result of the calcium H and K lines. So this cooling rate for one line, for instance, is the D excitations minus the amount of spontaneous emissions minus the absorptions locally in every place of the atmosphere. And using all the formulas that we've derived before and substituting that, you can show that this is basically equal to this term, which is typically how you would write radiative losses. This is your, in an MHD code, this is your Q, your radiative loss sinks and sources. Right? But you can easily show that it has to do with the difference between the excitations and the excitations in the line, which makes sense. So when you calculate that, and you calculate the radiative cooling for these different approximations, angle dependent PRD, CRD, and angle average PRD, you see that there are significant differences, and that here, for instance, in the middle chromosphere, the CRD has a larger cooling rate. And you can imagine that because in CRD, if you are a core photon and you get absorbed, you may be emitted in one of the wings. And when you are emitted in the wings, it's easier to escape. So the lines have a bigger cooling rate in CRD than in PRD. That makes sense. So it heats. You can see there's a difference here. It heats in the temperature minimum, and that's because photons actually. The reverse is true. When you have a lot of photons in the wing, they are mostly emitted in the line core where they are trapped. So there the line heating is stronger. But once you have an opportunity to escape, then CRD cools more. And there's very little difference in a hydrostatic model, as we would expect, between angle average and angle dependent PRD. I thought I had the dynamic. No. So what I did is I took a series of 20. I'm sorry, I accidentally deleted the slide this morning, but so I did a simulation and I took 20 snapshots from this radiant simulation that I showed you the time slices of. And when you do that, you get very similar results that CRD overestimates the radiative cooling. So to properly represent the radiative cooling by these H and K lines, you have to include PRD. It really affects the structure of the atmosphere. It's not only as important for line diagnostic reasons, it's also important for physical reasons, in this case, the radiative cooling due to these lines. And then let's have a break, and then we'll talk about these oxygen lines. So shall we start again? So the final example of how PRD affects line profiles is the case of the oxygen 130 nanometer triplet. So this is the term diagram of oxygen, and these levels here in red are at 130 nanometers. They have 3 different lower levels, and they share an upper level. This is an observation taken with the Hertz instrument, which flew on a sounding rocket and takes spectra. These are the line profiles of the 3 lines. And when you compare that with the line profiles calculated through a false model in CRD, you clearly see that you don't represent the lines very well. Maybe the relative intensities are reasonably reproduced, even though there is a central absorption and the observed line profiles, but that might just be spectral resolution. You don't know exactly. But you clearly see that the wings of the lines, except for this line, are not right in complete redistribution. So you think, well, I will just add complete or partial redistribution in each of the 3 lines, and that should solve the problem. We've seen in magnesium H and Ks and Lyman alpha that when we introduce partial frequency redistribution, the line wings tend to become narrower. But here in yellow, PRD, doesn't really solve the problem, right? Actually, the profiles change very little. So what's the case here? As I told you, it is important, in fact, that we have this common upper level. And so what can happen is that you can have excitation in one line, one of the three lines, and then de-excitation in either the line itself or in any of the two other lines. And this can be coherent. You have to account for the wavelength coherence from one line to the other. And formally, you can write this instead of this one expression, you have now to sum the contributions from all three lines to any of the other lines. So this becomes a sum over three lines instead of the line itself. And when you do that, lo and behold, it works. If you actually, this is slightly different. I'm one slide ahead. So one test that you can do is that the line that was where the difference between the observed spectrum and the calculated spectrum was the largest. You can say, well, let's just get rid of the other lines and just do PID in the line itself, where you force all the excitations to become de-excitations in the line itself and not have contributions from the other lines. And then PID does a very good job. So this is an indication that this cross redistribution, where you have coherency between different lines, is important. And when you do that, and you add the spectral resolution of the Hertz instrument, you see that you reproduce actually very well the shapes of these lines. So cross redistribution, if you want to use these oxygen lines as a diagnostic, you really have to include cross redistribution in the synthesis. Now this line has, oh, this is the last one. Oh, oh, it's a bit slow. If you look at closely at the term diagram, there's this lines here. Here. And you look at the wavelength of Lyman beta, there's a strong overlap. These are in very close to the core in the line wing of Lyman beta. So what happens, and because Lyman beta is very bright, you get excitation in oxygen to these levels, and then de-excitation, and you create actually a higher population in this upper level. So the source function goes up higher than it would be from the radiative transfer in the line itself. And that increases the intensity in these oxygen lines. If you would calculate these line profiles without taking into account this overlap with Lyman beta, you would get the red profiles here. So you would completely misinterpret the line profiles. That's the last slide I have for this. So are there any questions about the partial frequency redistribution? We can also talk about later. You can think about and let it sink in, and we can talk about it at the Q&A after lunch. But yeah.
Just curious about these profiles. I think we still see, even including everything that we have, this dips. I'm just curious.
Yeah, I don't know how to what the reason for that is. Maybe a one-dimensional model can never reproduce these reversals. I don't know. Certainly in the ultraviolet, you have very much nonlinearities with temperature. The source function in a 3D atmosphere is probably different than it is in a one-dimensional hydrostatic model. But yeah, it doesn't match. Oh, I can take my mouse. Okay, so now we can, if we can go to the second presentation, thank you. So we'll talk a little bit about the RH code. So as I told you, RH stands for the Rybicki hammer. So it is an implementation in as a forward solver. You have a model atom, model atmosphere, and you solve the radiative transfer for a multi-level atom. Actually, several multi-level atoms at the same time, in principle. And so RH is the implementation of those formalisms, and it does also LTE, because LTE is just a simple case of non-LTE, of course. And we'll see. You can also include molecular lines, and you can include polarization. But we'll go through a little bit of what the required input files are, and what kind of settings we can do. And then tomorrow we'll run the code in a simple case and look at the Python routines to read in the results. I don't know, Carlos, are you going to? Carlos is not here. I'm not sure what he will show in terms of desire, how you can set different things, but probably not too many things. So I think for multi-level non-LTE radiative transfer code, certainly when you go to more dimensions, there are two main options, which is multi-3D, which has an old heritage. Some of the publications about multi-3D are listed here. And then there's the RH code. This is the paper that where the method is described in the case of RH, where the implementation of the PID formalism in terms of the Mali iteration scheme is introduced. So typically, if you ever use RH, this would be the citation that you would use. So multi-3D is, as old heritage is well tested, is 1 or 3 dimensional Cartesian. A formal solution with short characteristics. It is parallelized very well by domain decomposition, and this is the big advantage of using multi-3D if that's what you want to do. And the partial frequency redistribution scheme was implemented as it is described for RH at a later time. So the RH code has 4 different versions: 1, 2, 3 dimensional Cartesian and a spherical version. Also uses short characteristic. It has natively the partial frequency redistribution. Zeeman effect by Zeeman, polarization by Zeeman effect is included both for atomic and for some molecular line schemes. There's also scattering polarization by continuum scattering, Thomson and Rayleigh. Molecular lines can be treated in non-LTE. This is most of the time not important because these lines are very sensitive to collisional excitation and de-excitation, because most of the transitions are because of rotations and vibrations. But for instance, for some CO lines, they are strong enough that non-LTE effects in the chromosphere matter. And we can solve multiple species in non-LTE at the same time. There's parallelization over wavelength if you work on a shared memory machine, and there's the option to parallelize in a 1.5D, where if you have a 3D cube, you solve every pixel independently. And this is there's a Python wrapper created by Ricardo Cafiera from Coimbra. So we talked about non-LTE. Non-LTE is important when density is low and the local conditions no longer provide the population number values. In LTE, of course, the radiation field is given by the Planck function. When the densities drop with height, collisions become less frequent and radiative transitions become more important. We've seen all that, how that works in scattering. So in that case, the populations are now determined by the local collisional rates, but also the non-local condition by the radiation field that comes from different places in the atmosphere, and also at different wavelength, different transitions. So in that case, we need to find a global solution not only in space but also in wavelength, and this is what RH is written to do. So when you download RH and you unpack it from the GitHub, it uses the following directory structure. It has a main directory, which in this I tend to call RH v2 because the original version, the v1, could only do one atom in non-LTE at the same time. But that's a long time ago. I started, by the way, RH in, I think it was 1994, so it's already quite old. I'm giving away my age, I guess. But so it is definitely an accumulation of effort that has grown and grown. Unfortunately, in the last 10 years or so, not as fast as I would have liked. But, so the directory structure is the main directory. Then you have the four different geometric versions. So typically, if you build the code, you build the two libraries here. There are some 490 functions, mainly because the code is written in C, and C doesn't have any internal complex arithmetic. So either you write multiplication and division in complex numbers as function, which tends to be slow, or you use the formulation in 490, and then you can just link them. And then when you build the code, you also have to run make in any of the four geometric versions. And so in each of these cases, the routines that are shared by the four versions are linked via the library, the .a files. There's a directory with IDL. There's now also a directory with Python routines. The IDL routines have a point-and-click GUI, so you can automatically read in all the output files and then point and click yourself through the different lines and comparison with the atlas. I'm not sure the atlases are included in the GitHub or not. I don't. But they are available, and if you ever want them, I can provide you the IDL routines or the Python routines that would read the standard atlases that allow you to compare average quiet sun at this center with your computed profiles, for instance. Then typically in any of these geometric versions, you would have a directory for a specific run, where you have a given atmosphere, a given model atom, for which you want to solve the radiative transfer, and you would create different directories for that, so that you don't override. If you want to compare one atmosphere with another, you don't override the results, because some of the output files have standard names, so they would be overwritten if you would run them in the same direction. There are three main input files: the keyword.input, the atoms.input, and the molecules.input. In the keyword.input, you specify which atoms.input file you want to use, and this is a list of atomic files that you want to use. Some of them will be used as background. They're called passive, where you just use LTE population numbers to solve the radiative transfer in that species. If you designate an atom as active, it will actually, for that atom, solve the non-LTE combined rate and statistical equilibrium and radiative transfer equations. Then similarly, there's a molecules.input, in which you can list a number of molecules. Typically, if you don't calculate molecular lines, these inclusion of those molecules affect some of the population numbers of your, for instance, carbon. If you want to calculate radiative transfer in carbon-1, it is affected by how much CO you form. So if you don't include CO in your list of molecules, you'll make a mistake because you'll overestimate the amount of, especially in a cool region like Penumbra or so, you'll overestimate the amount of carbon that you have. And this is generally true for other molecules, of course, as well. The chemical equilibrium equations that are associated with those molecules are set up automatically. So you always have to include H2 because H2 is part of the background opacities, the most populous molecule in the atmosphere. Although it doesn't, interestingly enough, it doesn't have any clearly visible lines because it's a symmetric molecule, and symmetric molecules don't have allowed transitions. All the lines of H2 are very weak. You can add to each of these molecule files, you can add a line list in a format that is defined in the code, in the comments. If you want to include, for instance, you want to calculate the G-band intensities, you can include a list of CH lines, and then the code will solve non-LTE or LTE, typically all these lines, and calculate the intensities in them. In that case, you have to specify an additional wavelength list, because for all the active atoms, the wavelengths are generated automatically because they have to represent properly the radiative rates. So you'll have to have, and we'll come back to that a little bit later, you have to have a proper cover in wavelength of all the line profiles that are important for your radiative rates. But for things outside, for LTE lines, molecular lines, you have to add explicitly a list of wavelengths for the code to solve. Then the third thing that is addressed in the keyword.input is which atmosphere you would like to use. And this includes in a separate file, typically the magnetic field. Of course, you need abundances for all elements, not only for the element that you wish to solve in non-LTE, but also for all the other atoms that are used as background opacity and emissivity. Then you can specify a list of LTE lines via the Chorus input, which is a list of files that has a list of lines, and these can be taken directly from Chorus's website, which you can easily find online. He has a line list over the whole spectrum that you can include in these calculations without having to change anything. The only thing that you have to be aware is that some of his files have an empty first line, and the code chokes on that. So you have to just remove that. If you ever run into a problem where the code crashes on reading one of these Chorus files, it is probably because it has an empty first line. Then the atmospheric files have typically, in general, the dimensions of the atmosphere. The code has some heritage in. When I started working in radiative transfer, my PhD was basically writing PRD for addition for multi, and when I did that, it was not done in a very smart way. So I ended up redoing that in what is now RH in a much better, I think, way and straightforward way. But there is some heritage of multi, and especially that is clear in the way that one-dimensional models are read. They are exactly the same format as multi 1D. And then for the 2 and 3D versions, I adopted a binary format, which is more compact and easier to read for larger volumes of data. But all of those dimensions and formats are described in the source files in the header of those files. So if you would go to read Atmos in .c in the 2 or 3D version, you would see exactly how you would have to specify an atmosphere for it to work. Or you can go to the IDL code or the Python code to see what kind of format is expected. Typically, the code works in SI units internally. And since I took over the multi-format for 1D, that is specified in CGS, but the 2 and 3 dimensional atmospheres are specified in SI units. So you have to be careful that you use the proper units when you read and use those atmospheres. Then the atmospheres, especially in the 2 and 3D case, specify the boundary conditions, the bottom and the top and the side. In the 3D case, you can only have periodic boundary conditions, but in the 2D, you can also have fixed boundary conditions on the side. Then you need the electron density. The code can calculate LTE electron densities. So if you take a simulation snapshot and you only have gas pressure of gas density, but you have temperature as well, you can calculate the LTE electron densities with the RH code. Then you need the hydrogen density. This can also be the total hydrogen density. And typically, when you, for instance, use a VAL model or a FAL model, those models provide the population numbers in different hydrogen levels. This is better for opacity, background opacity calculations, because they tend to be non-LTE values. And the H- opacity, for instance, depends on this kind of, on the ionization of hydrogen and the electron density. But if you don't have that, you can specify that you should have hydrogen in LTE, and then the code will just solve the Saar-Boltzmann equations for hydrogen and use that for the background opacities. Then you have microturbulence. Typically for a 3D atmosphere, you don't have to include any microturbulence because the convective velocities add up to enough broadening that you don't have to use the artificial microturbulence parameter. And then you have macroscopic, the flows represented by the velocity. And then in a separate file, and this has, again, is for historical reasons, they're not, these magnetic field values are not included in the .atmos files to be compatible with the multi-format initially. I mean, it would be easy to change, but it would just make backward compatibility a pain. So in these .b files, you would specify field strength, field inclination, and field azimuth. I believe in radians, but I don't remember exactly. Again, that's specified in the source files. Then, if you look at any of the .atom files, it has at the top of the file the ID, the element, Ca for calcium, etc. It specifies the energy levels, the list of bound transitions, the list of bound-free transitions, and all the collisional cross sections that you need. Ironically, to do non-LTE radiative transfer properly, you need good estimates of the collisional cross sections. Well, if you have a lot of collisions compared to radiative transitions, of course you have LTE, but to do non-LTE properly, you need both the radiative line strength and the collisional cross sections, and those are typically not so easy to find. So for each of the energy levels, you have a statistical weight, you have a level label. This level label is used. You have to, if you do polarization, this is important because it tries to infer the proper quantum numbers for J, L, and S from the level designation. And it has to have the ionization stage. For the bound transitions, you have the level IDs, so between level 2 and 3, for instance, like Carlos was showing, that you need to assign a level to the line list in Desire. You have the oscillator strength. You can specify with line shape. You can specify void profile or Gaussian profile, or you can specify PRD. This is a bit misleading because in PRD, the absorption profile is still a void profile, but the emission profile is determined by the redistribution function, right? Like I showed earlier today. But the designation, just to make it one keyword, is either void, Gauss, or PRD. Then you have to specify the wavelength grid parameters. So you have to specify in Doppler units how wide the line is and how wide the region of the line core is. And this matters for the wavelengths that are chosen. As I told you before, you have to make a proper choice of wavelengths so that you can integrate the line over the, so basically you can integrate the J bars that we talked about yesterday, which is the intensity over the line profile integrated in angle and wavelength. And so that is not left up to the user. That is typically given by two parameters that then distribute the wavelength points 50-50 between the line and the line core and the line wings. But where that transition is between line core and line wing is a separate parameter. And then you have to specify the cross sections for van der Waals broadening, Stark broadening, and this can be done in different ways. Recently, we implemented also because of desire, we implemented the bar-clamp formalism, so you can specify which formalism you use for the van der Waals broadening, bar-clamp or Unsold, or there's another one, and you can specify then the coefficients for that broadening that determine the dependence of temperature on the damping as a function of temperature. Again, here also you can either have hydrogenic, where you just specify, so for the bound-free condition, the transition, you specify either hydrogenic, which means that you just specify the bound-free cross-section at the ionization wavelength, and then it's wavelength to the third or nu to the third for shorter wavelengths as the cross-section, or you can explicitly specify the ionization cross-section for different wavelengths. This is important when you have resonances in your ionization cross-section, or a very different shape than hydrogenic, and that matters for the ionization rates, of course. And then you can specify the different types of collisions and their temperature dependence. Let me just show you some examples of different keywords. So this is a example keyword, and we can briefly go through it. So the atmosphere is specified here, the file with the abundances. We talked about the number of rays, which is for the angle integration here, and it's the same in desire. The atoms.input file, the molecules.input file. The wavetable is a file of additional wavelengths. There's a very rudimentary manual in the distribution, the .pdf file, that actually describes in more detail how you write these .wave files. When you start iterating, there is some scattering in the background because of Rayleigh and Thompson scattering. So this number specifies how many iterations. Actually, these are lambda iterations. Before you start changing the population numbers, you just do a few lambda iterations to get this background scattering properly redistributed. This has to do with the statistical equilibrium. Typically, you leave this to -1, where the code decides. In the statistical equilibrium, you always use a separate equation or a closing equations, which is the sum of all levels should be the abundance times the hydrogen number, right? You should always have the proper number of hydrogen or proper number of atoms in a given species. And so this ISUM determines which row in the statistical equilibrium equation is eliminated by substituting it with this closure equation. Some of this is exactly the same as multi-heritage, obviously. This is the the number of non-LTE iterations, the maximum number. So the code will just stop after this number. Typically, this is good. If you have more complicated atmospheres, you might have to iterate more than that. This is the iteration limit. So these are after the code reaches relative changes in the population number that are smaller than this value specified here, it will stop iterating. It will consider the solution converged. Then there's this NG acceleration that I told you about earlier. You can set 3 parameters for that, which is the delay. So it will do 15, in this case, 15 iterations without applying the NG acceleration, and then it will use it. And there's no sense in applying the acceleration every single regular iteration, because you just use duplicate information. So it's better to let the code iterate the number of times that is specified as the NG period, in this case 3. And in the case of the order, it uses 2 previous iterations to find a more likely solution, but, as specified by the NG acceleration mechanism. Typically, if you don't want any NG accelerations because it messes up your convergence, which can happen if you accidentally create negative population numbers, you would set NG order to 0, and that would then it would just iterate. RH formalism. These are PID, so the PID max iteration is typically set to 3. This is the internal loop that iterates over the profile to get the redistribution right. This is the inner loop that I told you about earlier in the scheme. And this is the limit after which it stops in relative changes in the intensity. So if your iteration, if you do 1 PID iteration, this inner loop, and the changes in the intensity are smaller than 10 to the minus 2 everywhere, it will do less than 3 iterations. And then you can also, this PID iterations, you can use NG accelerations. It typically doesn't work very well, but it's an option if you wish to try. Then you can specify whether you want to do angle-dependent PID or regular angle average PID. You can specify if you have an oxygen atom, and typically it will only do PID in the line itself. But if you want to account for this effect that we talked about, where you have this cross redistribution coherence of going up in one line, going down in the other, then you have to turn on this XRD, the cross redistribution. These are just some file names that you can specify so that you don't use the default names. You can actually specify metallicity, where all the abundance different than hydrogen are scaled by a common factor. So if you want to do a quick calculation in a metal poor star, you can just set metallicity 2.4. Or whatever value you wish to choose. Then this, you should not change this. This is the partition function values that are used to calculate the LTE populations for all the background atoms and the ionization fractions. Then you can specify this corus.input file, which is the list of files that have line lists. And there is a simple, so some of these lines, if they overlap with very strong lines like the magnesium or calcium lines, these additional opacity from the line wings of these strong lines causes the normal lines to form very high in the atmosphere, where they already start to sense the chromospheric temperature rise. And then this may, if you assume LTE for these lines in the line wings, you'll get emission lines. And this is a simple mechanism that implements just the monochromatic scattering for these lines. So monochromatic scattering is exactly the same, is the 1 minus epsilon j plus epsilon b formalism. In that case, you get rid of this emission, which is not natural. So this is the number of iterations that you would normally use. You can specify whether you want to solve for the electron density. This will give you the LTE electron densities in the atmosphere. You can specify whether you want to assume hydrogen in LTE or whether you want to read in different hydrogen populations that you get from your model atmosphere, for instance. You can solve for hydrostatic equilibrium if you wanted to. And then this mostly determines whether you write some of the opacities to a file. These are the opacities from active elements and the radiative and collisional rates and the damping parameters. This is this P micro characteristics is a characteristic microturbulence that you use to scale actual wavelengths to Doppler units to see where the wavelengths fall that you specify in the dot atom file. So by changing these parameters, you will change the parameter, the wavelength grid of your lines. Then there's this parameter. If you wish to ignore Doppler shifts, you can set this to some value, and any Doppler shifts below this value are ignored. So typically you would set it to 0 so that you account for all Doppler shifts. But if you do, for instance, say that you want to calculate from a 3D simulation, you want to calculate the G-band intensity. The G-band intensity is the integration of all the CH lines at 430 nanometers over a filter that has a typical width of 1 nanometer. Doppler shifts don't matter for that. But you spend, if you go at different angles, you spend a lot of time calculating line profiles because you have to calculate a different line profile for every different angle. And if you want to not spend that time, you can just set this macro threshold to a larger value and therefore just ignore all the Doppler shifts and still get a good value from the G-band. So that's why this parameter is there. You can specify a reference wavelength. Typically, of course, we compare things with optical depth at 500 nanometers. So typically you would by default use the 500 nanometers. And you can specify whether your wavelengths are written in vacuum or air. Typically you would leave that to air because you would get wavelengths that you don't recognize for lines that you know. Then there's some Stokes parameters. You can specify the atmosphere, the magnetic field part of the atmosphere. You can specify, we talked about this yesterday, this polarization free option no longer exists. It was not that useful. So you can either do no Stokes field free, where you solve the radiative transfer equations, the Non-LTE part, by using the approximation that the line profiles are not affected by Zeeman splitting. And you only solve for I to calculate the radiative rates. And then once you've reached the converged solution, you recalculate the line profiles, including polarization effects, and you solve for the full Stokes vector. Typically, when you have the Zeeman effect and you have a strong field, the line grid is no longer matching the place where the different components of the line profile are. So you can introduce some kind of a characteristic magnetic field strength in this. So the fields are specified in Tesla, and then it will redistribute the line wavelength grid around the centers of the shifted profiles at this characteristic magnetic field strength. So it gives you a better wavelength sampling for, and when you have large line splittings. You can, for the 3D, sometimes you can specify background polarization. So it would include calculate linear polarization as the result of scattering in Thomson and Rayleigh scattering. And you can limit memory, which will write some properties like absorption profiles and the values for the angle average mean intensity, which tend to, so line profiles scale with the number of wavelengths, the number of spatial points, and the number of angles. And then if you have polarization times 7. So that's a lot of memory. And if you do a 3D calculation, you may just want those as temporary files rather than occupying memory. And that is what limit memory will do here. Sometimes it is effective to eliminate all contributions from lines that you have in your .atoms file that are specified as passive, that are just serving as background lines. But if you want to ignore those lines because you don't want to spend the time calculating all the absorption profiles for these lines, you can specify this as true, as false. And then you can parallelize in wavelength, and this is the number of threads that you would use if you do that. So if you have a machine that has, I don't know, 16 cores or so, you can specify 16, and then when you do the formal solution of the radiative transfer equation, it will solve 16 wavelengths in parallel. Okay, so that's the keyword file. Then if we go to just the sample.atoms file. So it's just a list of atoms, some of which you can specify as active in this case. The code will try to solve for hydrogen and oxygen, non-LTE. And this is, for instance, if you wish to calculate these 130 nanometers line profiles, then this is the setup that you would use. Maybe you would add more lines, more atoms, that's okay. And then you have an initial solution, typically for lines that have, for atoms that have strong lines. Zero radiation field works well. It just solves as an initial solution the statistical equilibrium, assuming only absorption and spontaneous emission and collisional transitions. Or you can use LTE, where it just solves Saar-Boltzmann as an initial solution, and you iterate from there. Then finally, the simplest case is the you can just put a line of molecules, and as I told you, you can solve for instance, carbon monoxide in non-LTE wish, but you can just add any of the molecules as long as you have the molecular dissociation and the parametrization as a function of temperature for the partition function of the molecule. Those you can find, and there are papers that are there's some of these papers that have these lists are listed in the code, in the header of the code. So I think that's what I want to talk about here. So Carlos, do you know, are you going to show more about input parameter, different input add for design? Yeah. Yeah, but so at least they hear it twice from different, and maybe it becomes clear. Any questions? Did everyone manage to install RH and try any of the examples?
A question about running in an MPI environment with that n.threads parameter. So would you typically use multiple cores?
So
on your MPI?
these are just an implementation of POSIX threads. It doesn't use any MPI.
Okay. So each MPI task would have to have multiple threads if you wanted to do multiple wavelengths.
Yes,
with
as long as you have
threads.
access, as all these threads have access to common memory.
Right. Okay.
Just as a note, the Python wrap that we use for share and desire for running in parallel, that essentially takes a cube, then distribute it between cores and then read the results. It also works with RH. So in principle, we have a wrap that we're able to, if you get the atmosphere, you give it to the code, it will distribute it in cores, and then you will get the profiles from there. I'm sorry, I will explain it later for this side and also for RH. In that case, when you are distributing the computation between cores, it's important to keep one in the keyword input for the parallel, because otherwise you're distributing the computation of wavelengths between cores and the computation of different atmospheres, and it will get confused.
Okay. So we have a break now. Okay.
Then let's start again. Yesterday, we stopped just at the beginning of tutorial 4. So I think it's fine if we just quickly start from the beginning. So then the idea is that in tutorial 4, we are going to combine everything that we have done in the 3 previous tutorials. So in the first one, we created an atmosphere. We defined the wavelength range that we wanted to compute, the different spectral lines that we wanted to synthesize. In this case, we also specified which transitions we want to solve in Non-LTE and which transitions we want to solve in LTE. And then we ran the synthesis. And after that, in tutorial 2, we took those the stocks profiles, and we added noise to them. Okay. And after that, in tutorial 3, we checked again how to define an atmosphere, optimizing the 3 elements. So a good number of optical depth points that will allow us to have a wide range of nodes options, good height coverage that will allow us to compute response functions for the spectral lines of interest and in a range where they are large and where the lines are sensitive, but also beyond that, so to allow the response functions to go to 0, even if we have complex atmospheres. So then after that, we went to tutorial 4, that is where we are now. And here we are going to do the inversions, and we are going to play a bit with different configurations. Okay, so then what we need to have in this tutorial to reproduce your example is the profiles that you have in tutorial 2. That in each case is different because someone is using 6301 and 602, someone is using 6173 or 5250. Okay, so you copy that profile here, then the initial atmosphere from tutorial 3, that also maybe some of you changed a bit the atmosphere. And then from tutorial 1, you need to copy the grid file because you change it for synthesizing 50 to 50, 6173, or 602, or 1.5 micron. And with that, in principle, you should be ready to go. And then in my case, remember that I let it go. So I was running the code here. So I will run it again. And then I was just running 2 inversion cycles. And then I read the profiles for 8542. I said that the first plot was nice, but in this case, we want to really be sure that we are fitting the core of the line. So then the first plot that I want to check is 1, so 129. Okay, so then I will do this. Then the code is a bit slower compared to SER, but still it's fast. So it's doing 2 cycles. And now it's done. And this is the plot for the central part of calcium 8542. Okay, so did everyone reach this point? Okay, so then I guess someone had not so good fits, but I think already we checked, for example, Vincent, and I think also in the front part here, we also, your name was, I always forget, your name is Willis, Will. So Will with 50 to 50 worked well, then Vincent with more relaxed magnetic field also was working well. But for example, Nancy said, mine is not fitting well, but I saw that after that she was playing and now it's fitting well. So can you show it to us, your results, and also tell us what did you change to improve it? Okay, that's good. That's good. Okay. Yeah. Yes, 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 no problem. So also if, yes, yes, I usually close everything, mail and things like that, and then I share everything because if not, I get confused with which screen I'm sharing. Okay, it's fine. Yes. Okay. Okay. Okay, so yeah.
So it's like 5 cycles or 4 cycles now?
Yes. Yes. Yes.
And
No, it's fine.
so then I.
Okay. 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 So then before going to the control file, so then let's go step by step. So this is the next plot of the script. So here already she's showing us how the profiles evolve in each inversion cycle. So colors are different inversion cycles, and I guess probably blue is the last one. Okay. So then in Stokes I, it seems that since the beginning more or less is getting there, but it's clear that, for example, in Q, even if it's not exactly perfect at the end, but it was bad at the beginning and it's slowly getting there. And the same with the Stokes B. So it was a bit bad and probably almost the rest of the cycles, the code was changing mainly azimuth or the inclination. Well, not the inclination because it was already good. So probably in the last cycles, it was changing the azimuth to try to also get a good fit there. So then here is not just the last cycle. So she's showing us different cycles. Okay. So this is one thing. So then for this configuration in the control file, she already put one in the sentence that says, I don't remember, right. What was the sentence in the control file? So can you show us the control file? Yeah. 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 So just okay. So just go to the end. So what I was saying is that here she's using one, so then it's saving each cycle. If you put 0, then it will be just the last one. Okay. So then so far, so good. Is it good? Yes. So in this final evaluation of profile, the code by default can run several cycles, and you can decide if it saves the atmosphere and the profile and eventually the error for each cycle, or if you just want the last one. Because I think initially you will do some tests and check if adding one cycle is improving or not. So then you can compare as Nancy did. So maybe you can decide that between the blue and the previous color, I think red, there's not so much improvement. So then you can say, okay, I will just stop in 3 cycles instead of 4. But then when you have your configuration ready, I don't recommend you to write all the profiles for all the cycles, because you will just use the last one and you will save time, and you will also avoid writing more on this than necessary. But if you are doing tests and you want to check if you need 4 or 3 cycles, for example, it's good to put here 1 and then just plot all the profiles and check that if you see an improvement every cycle or not. Okay. Okay, so then let's go up and see what is your best configuration. Okay, 4 cycles. Okay. Yeah. Yeah. So it improved with that. Okay. Yeah. Okay. Okay. Yeah, that's interesting. I don't usually do this, but at the same time, I said between yellow and the rest of the colors for stocks, I didn't see too much differences. So it means that the code was already getting a good fit after the first cycle. So it's an option. I usually go step by step, like 2, 3, 5. But if in this case works for you, then it's fine. That's okay. Yeah. Yeah. Okay. Yeah. 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 I think there's no rule of how you do things. The only recommendation I always give is if you have a map, 100 times 100 pixels, for example, then randomly pick like 10 pixels and do this exercise. So if this works for all the pixels, then you have your configuration ready, and then you should embed the full map with that configuration. If it works very good with 1 pixel, but not so good for like the other 9, then just go back and play again until you get a balanced configuration for like 10 pixels that are corresponding to different solar regions. Okay, so then micro, it's 1, that's okay. And then here, just one thing. So if you just write 5, 6, and then you don't write anything about that, it will always pick 6. But this way, you are definitely sure which one is using, so it's fine. Both options are fine. And then I see that it's reasonable to go to 5 and then 6, and then the inclination it's also 3 and 2. So I think it's very good. And what I was saying yesterday to Nancy, and also I told her just remind me to say it here. So the idea is that this is essentially what the code is assuming as inversion parameters. And the idea is that then you have the free parameters. So the number of wavelength points times Stokes profiles is what you can assume as a free parameters. Well, sorry, is what you can assume how the code calls it. Yeah, free parameters. And then here is the number of nodes. So my recommendation is that you should try to keep the total number that you have here smaller than the number of wavelength points that you have. So for example, now we are simulating a spectrograph. So we have like 200, 300 points per spectral region. But if you go to an imaging instrument, usually you can have like 4 or 6 wavelength points. So then if you have like 6 wavelength points times 4 Stokes parameters, here you have more free parameters and the combination of wavelength points times Stokes profiles. And there you can enter in a region where it's probably not best to enter. So then my recommendation is if you have a spectrograph like this, imagine VISP, then you can definitely do this or even more. But if you are with an imaging instrument, then try to keep things a bit more conservative, because otherwise you will have more free parameters and wavelength points. Did you follow this? So just again, so imaging instruments, they have a very narrow filter where they fix a wavelength region, and then you have a 2D field of view. And usually they do that like 5, 6 times per spectral line. So then essentially your profile has 6 points or maybe 8 points. And this is much less points than the one we have now. Like we have probably 200 or 300. So then there you need to balance between the number of free parameters and the number of wavelength points that you have. Okay. And did you play with the initial atmosphere, Nancy, or use the same one? Did you also change it to check if it works, or you? Yes. Okay. So do you remember which one helped you to get the best result? It was like with a given inclination or with a given velocity? Yes.
But then I just increased it,
Okay.
kept it constant.
Okay. Okay.
If that's right, it's one.
Okay.
Okay.
Good.
But then I compare by
Yeah.
4 to 6 kilometers per
Okay.
second in the
Okay. Okay.
out of this precise exercise.
Closer to it. Yeah.
Closer to that.
Okay. Good.
Sure.
Good. 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 Perfect. Thank you. So then, does anyone wants to also show? So did you have problems and then you solved it playing with the configuration? Someone wants to show that? Yeah. Simon? Yeah. Yep.
There you go.
Yes. 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 So I prepared very quick overview of the how to prepare initial atmospheres. I will show it now. But I would say that in this case, you are able to really go back and check that is accurate. And in general, you will not be able to do that. So then I would recommend always positive and negative velocities. And then the amplitude, you can even play with two values like 1 kilometer and then 4. And then I think with that, you will not see difference if you then add 6 or 7. It will just probably work. But essentially, I think minus and so positive and negative velocities should just cover most of the spectrum. And even if in this case you feel that it's getting closer, if you choose then at random pixels in your map that they have a low velocity, you will see that maybe the fits are worse. So it's just in this specific case. So in general, my advice is you take like 10, 20 pixels, and in average, you get good results for all. Because if you focus on one, then you may be not getting good results for the others. So always try to get a balance. And in the case of having really different solar structures like sunspot, penumbra, and white sun, one may even think of doing a specific configuration for each case. But still, I think that if you try to fit them all together, like a pixel from the umbra, a pixel from the penumbra, and a pixel from the white sun, and you find a balanced configuration, I would recommend to use just one for the full map. Okay, like that. Yeah. Yep. Yes. To the weights, yes. 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 Yep. Yeah. 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 Okay. Mhm. Maybe you can take the microphone, Simon. I think you can take it with you if you want to. Or yeah.
I was saying that that profile is really sensitive to weights for some reason. So I don't know why, but this with this set looks like reasonable at least the shapes, but this is still not working with the amplitudes. So this was the best thing that I can manage. But I think that I have to change also the initial atmosphere. I haven't done that. So yeah, basically that.
Yeah, thank you. Yeah, I think in general, even if it doesn't sound too good, weights are really, they have a strong impact. So if you want to fit 3 profiles that are different and you want to fit them the best you can, you probably need to have different weights. But again, my advice is to try to fit them with one configuration. If you can do that, then it's really good. And if not, then probably you need to experiment or to separate configurations. But in general, yes. So changing weights is going to really move you from maybe a very good inversion to a very bad. And sometimes it's not so easy to know which one you need to weight. Because sometimes, as we saw yesterday, one tend to assume that, okay, if I want to have a better fit for Q, U, and V, I need to put more weight there. But then you are fitting wrong or poorly stocks I, and then this affects all the fitting. So sometimes it's better to focus on the stocks I, and this will just cascade to the stocks Q, U, and V. So it's not easy. So my recommendation is that before running any map, pick pixels, play with them, because even if you spend 1 week playing with the code and until you get a configuration that is reasonable, then you will run over a full map, and then you will need like 1 month or 2 months to analyze the complete results. So it's not bad to just at the beginning try to find something that is balanced and works for in general for all the pixels. Okay, so then before that, before continuing, I was checking this morning. So day 9, the Design Online tutorial. This is, sorry, I'm sharing, but it's not. Yeah. So in day 9 of the Design Online tutorial, that is the last one, I explain how to take atmospheres and from there create a set of initial ones. So you can go there. It was before I started to use Python, so it's in IDL, but the concept is very simple. So there's a folder. So if you open this atmosphere.zip, there's a folder with input, And here you have, we have a set of atmospheres of FAL models. So FAL C is quite sun, FAL F I think is flash or faculaire, H I think is flash, and there's P, I don't remember if it's penumbra, and then R I think it's umbra. So you have a lot of models. And then you have also the VALSI, the HSRA, and also the MACL. So you have multiple atmospheres here where they have been created for reproducing the solar atlas, but averaging in different solar scenarios. So then you have from quite sun to umbra. So then the idea is that what I do for current inversions is that I take, for example, FAL-C, and it doesn't have velocity or magnetic field. So then I put a positive velocity and a magnetic field with a polarity below 90 degrees and with an amplitude of, I don't know, 200 Gauss. And then, well, let me show you. This is ideal, but essentially the process is the same, but just in Python. So then I take FAL-C, and then I add, for example, this configuration. So I have a 200 Gauss magnetic field, positive velocity, and incline, parallel to our line of sight. And then I save this as with this name. Then I will show you later why. And then I read it again. But now I put, for example, stronger field. Now the velocity is negative, and now the polarity is the opposite one. Okay, and then I save it with this name. Then I go to HSRA, and then I go to file, then another model. So I just start combining all the models that you have there with a given velocity and magnetic field. And then I create a library of atmospheres, and they are all called ATMCL something, number 1 to 12. And then I put this in the parallel wrap, that hopefully I will show you someday how to do it. And then I tell the code, use all those atmospheres to repeat the inversion of each pixel and get the best result from there. So then I'm using a library of atmospheres that covers a lot of thermal scenarios. So the relation between temperature and electron pressure is different between FAL-C, MACL, or VAL-C. And then I'm also providing different magnetic field and velocity. So with this, in general, what you get, I'm doing an inversion. I think this is probably Nancy's data. I don't remember if it's your data, but it's SST data. And this is the chi-square values that you get the top from using one atmosphere. That is already good. And then in the bottom from using 2 atmospheres. I don't know if you see it very well there. If not, check it in your laptop screen. But I think you're seeing all these black dots that they are isolated. The big ones that I have problems and I need to check with the configuration. But the isolated ones, the code didn't work, but it's just for a few pixels. But then if you go down, for the example with 12 atmospheres, same configuration, but just different atmospheres, then you see that things here are much smoother. Then the problems that I had here, they are much smaller here, or at least the area of pixels that didn't converge is much smaller. And then also here is much smoother. You can see it in your screen, or just go to the Dropbox folder and download it. So then there are several steps. So first, playing with the configuration until you get something reasonable, and then after that, playing with the initial atmospheres, so you can get better results, but also smoother results in terms of 2D. Because some pixels cannot work with one atmosphere, but then if you play with 2 or 3 different atmospheres, suddenly you can get much better results. For example, look at this corner and then looks here. Okay. So then you have the tutorial there. I promise I will just prepare the same script in Python soon. I will send you an email just with that date. But essentially, I think you can do it now. So just use the readwrite.py routines to read the atmosphere and then modify it. And then if you want to play already in serial, just start from different atmospheres and then read the chi-square value and compare it between the 3-4 runs and take the best one. Okay, so you create a loop, and then inside the loop, you are calling the code several times with the same inversion configuration, but they're starting from a different atmosphere. And then you save the profiles, the atmospheres, and the chi-square values. And when the loop finishes, you compare the chi-square values from the 3 or 4 iterations, and you pick the best. This is one way of doing it. Then in parallel is much easier, but just if you want to start trying it. Okay. So then, yes, okay, yeah.
Curious that same structures here and both of the panels, there's some of the same structures that have the, I guess, like low chi-square. Guess what are those?
You mean the black?
Yeah,
structures?
the
I think they are regions with complex magnetic field in the observation. I think the gradient is large, so the velocities are a bit complex, and the profile is also complex as well. So I think probably I need to, or we need to improve a bit the velocity configuration. So I mean the number of nodes for velocity and magnetic field to probably get better results there. If that doesn't work, then we need to go one by one and check why the code is failing there, because it seems that it's just in this area. So probably I would set configuration for now, maybe not enough degrees in field or velocity. But if we still don't get good results after changing that, then I would go one by one and check maybe there's another issue. But essentially, I think there we have like flash, and then it's a bit complex. Yeah. Okay. So then, if you want already to give it a check, just go to day 9 in the tutorial. You have the recording also where I explain how to do it. And this atmosphere is what you have inside. Just one thing, and this is for the parallel wrap, but I guess, yeah, and this is for the parallel wrap. So, as we're going to do the inversion comparing atmospheres, and we want to save all the results in the same array, I interpolated all the models, the same optical depth and the same optical depth of points, because otherwise creating the array for all the pixels is going to be difficult. So I already did that, but just in case if you pick another atmosphere from somewhere, just be sure that your ATM CL models, they cover the same range and with the same number of pixels, because otherwise you are not comparing just a different initial atmosphere, you are comparing other things, and then you cannot save them because it's difficult to create an array that is changing with time. So the array where you're going to store the results should be constant with time. Okay, I think probably in the future I will just ask you to attend one tutorial, and I will make 1 hour telecom, and we can just learn how to do it together, and it will be easy to follow. But I just wanted to say that it depends on weights, it depends on nodes, but also it depends on the initial atmosphere. But we know that, and we already take this into account when running an inversion. And before I continue, I said that if you want to do it, you need to compare the chi-square values. So they are saved here, okay? The inversion.chi, it's saving the results of the chi-square values for the last cycle. And use this one, the second one. I always forget what is the first one and the other one. Just use this one. And the important thing is, if you want to compare chi-square values, like for example, when you are using different atmospheres, it's fine to just read this value and pick the lowest one. But if you change the configuration, the number of nodes or weights, then you cannot compare. Because this chi-square is not the traditional one where you get good results with 1 and you get bad results with 0. This chi-square contains information about the weights, the number of nodes, and different things. So at the end, for one configuration, if you use different initial atmospheres, you can get the best result with the lowest value. But as soon as you change nodes, this value is different. So I can show you eventually how to get to this point, or if you want to do it quickly, just you can compute the chi-square by hand. So you take the initial profile, you take your output profile, and then just compute the difference. And then if you change the configuration, you will get another output profile. You can compute the differences, and the one with the smaller difference is the one with best results. But in this case, it's because since the SER period, that chi-square contains information about the nodes. Also, it's affected by the signal to noise value that you put in the control file. It's mainly also included here. So then it's difficult to compute this value for a given configuration and compare it with others. So for doing automatically, just keep the configuration constant and then compare those values. And if you want to change configurations and evaluate which one is producing the best fit, then you should do it probably by hand for now. I'm talking already with Basilio to include a fourth column that is the traditional chi-square 1 is good, chi-square 0 is bad, and this will be the one for all the configurations. But this is ongoing, but soon we will have it, precisely because of that, because it's confusing to know which configuration is better if you change the configuration of the nodes and weights. Okay. And then to avoid making things complex, if you want to run 3 atmospheres for the same configuration, save this value in every run of the loop, and then take the best one, the smallest one. Okay. Okay, so then close this. Then we go back to, yes, tutorial 4. And then in my case, I said, okay, we have been playing with the calcium. Yes, let me close this. With the calcium line. Just let me go back and so calcium is fine, but then as we are embedding 2 wavelength regions together, we also need to check that the iron lines are well fitted as well. So in my case, it's perfect here, very good here, still more or less, but still I would say that this is very nice. And then here it's okay, just because this is 1% and this is almost 20. So I would say that in general the fits are good and they are compatible. So, I mean, we are going. So it means that we are getting the atmosphere with high accuracy in lower layers because we are fitting these lines, and also with high accuracy in upper layers because we are also fitting calcium. Okay. No question? Yeah.
How is Stokes V so polarized and we don't see anything in Stokes I? Seems a little bit counterintuitive, but I'm not sure.
I don't know. So I think the magnetic field is not so big, and the temperature is relatively normal. So I think it's fine. It's very vertical, probably. No. No, I think it's because the magnetic field is not very strong, but it's very vertical. So then, and micro turbulence is 0 and macro as well. So it's very narrow. And I think it's because also I think it's not so strong. I don't remember. Just let me go back. Tutorial 1. It's 600 Gauss. That is still weak field regime for those lines. But I think it's because there's no macro, no micro, and also because it's inclined. So I have 45 degrees. Well, not really vertical, but still not very inclined. So I think it's just that. Probably with a macro of 1 kilometer or a PSF, this would just go down to 10% or something like that. Or with higher temperature, because I have almost HSRA, but if we make this a bit hotter, like a bright point, then we will see the splitting much better. Okay, yeah, thank you for the question. So then I will just save it here. So then, did some of you got good results for calcium, but bad results for the iron line? Or in general, if you improved the calcium inversion, it was also improving the iron lines inversion? Okay, Saida is not a comment. Okay, okay. Yeah. Okay. 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 But later we can check a bit more. We can fine tune a bit, and I think we can get good results for calcium, and then probably we will also translate to iron. Okay. So then let's proceed a bit. So move this one, and then in the control file, we probably have it ready. I think. Well, yes, let's stop here. So now I'm going to show, as Nancy did, so the evolution of the inversion. Yeah. Well, I think I have it. Yes. So I will remove this one. So I want to show you the evolution, but just in line core wavelengths, because it's where you really get to see the difference. Here. And this one, no, this no, and then this one. Okay. So here we are plotting the profiles that we get from the first cycle, and then the profiles that we get from the second cycle, and just in the line core wavelength region of the calcium line. So then in my case, you can see that when we started, the wings were not well fitted because the blue line is getting lower and here also lower. And then the core was not so good. And then in the second cycle, now the continuum looks, well, the wings looks very good. And also the continuum was very nice. And then here we are getting almost on top of the line. And the same is in the rest of the line. So you can see that here, I think red is not great. So blue was bad. And then this part, we get it a bit better. But still red is not exactly matching this one. So maybe in my case, I may need another cycle. Even if I got flat, so I use a constant magnetic field as an input. Sometimes with another cycle with like 3 nodes, the code can just make small curved line, but not with a high curvature, and usually can get better results. But still, I would say that is fine. And you can see that between cycles, mainly in intensity, was changing a lot. Like for example, in the case of Nancy. Although in her case, for me, it's interesting that starting already with 5 nodes in temperature, it allowed the code to really move to the best solution for Stokes high from the second cycle. And then after that, it was not improving the Stokes high, but it was improving the other parameters. So it's good to try those things. And if it works, then great. So then let's move to the next one that I think is where I want to spend more time with you. And is so this is iron lines. I think we don't need to check them. And this is weights that I think you already have under control, at least the concept. So we are not going to play with weights, and I will show you how to work. So just we can end this exercise and move to tutorial 5. That is where we are going to compare the atmospheres. Because right now we are getting good results in general, but now we should check if this fits of the Stokes profiles translate into recovering accurately the atmosphere. Okay, so before moving to tutorial 5, any question regarding tutorial 4? No? Okay, so then let's move to tutorial 5. Let's open it, and then here, let's slowly check what you need to get. Okay, So you need, because we want to compare also how far we started from the, yeah. Yes. Yeah. Yeah. Yes. 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 Yeah. Yeah. So it's very simple. It's what we did last week. So now we are going to take the initial atmosphere just to check how far we are from the final point. We are going to copy from tutorial 4 the final atmosphere. That it will depend in your case. So for example, Nancy was 4 cycles. In my case, it's 2 cycles. You take that atmosphere and you copy it in the folder. And then in this case, in principle, we should also add the error. But as I said, I don't understand why it's not writing it, but I know that it's not doing it. So I will try to fix that with Basilio next week. And then you need to get from tutorial 1 the atmosphere that you use for the synthesis. So we are going to compare the atmosphere that you use from the synthesis in tutorial 1 with the atmosphere that you got in tutorial 4. And just as a context, we will add the atmosphere that we use as a starting, as a guess atmosphere that you create in tutorial 3. So 3 atmospheres. Okay. And we don't have errors for now.
We're just wondering if anybody has any questions from this morning or last week. Kevin is here. If you have instrumentation questions, today's your day. Or even inversions in general. Not if you have questions for Carlos, he's gonna start up in a few minutes, so you can wait for him. But anything. If not, that's fine, and we can move on. I think Marcelo's getting up. Guys too.
So if you would look under the hood of a code like SIR or Desire or RH, you would see that there are a number of background processes for which you need densities of specific particles. One of the major one in the photosphere in the visible wavelength is H minus. So what goes into that is you need to have the H minus ionization potential, which is 0.754 electron volt, and you need some equilibrium constant to see how that concentration changes with temperature and so, and then you need a cross section, and so there are routines that will do all that and calculate the opacity of those kind of processes in the background. There's Rayleigh scattering, Thomson scattering, so it all involves collecting the cross section, the most up-to-date cross sections that you can find for these processes, finding the right densities of the right particles, and then what else is there? There's H hydrogen 2. There's hydrogen bond free opacities. There's there. So there are a number of atoms that you include in the atoms.input file that you set passive, and they actually contribute, especially bound-free opacity in the ultraviolet part of the spectrum. Something that is also most of it is in the background because you don't see the bound-free transitions as a spectral line so as easily. So there is actually in RH a possibility to calculate the individual contributions and tabulate them and make a plot. There's actually even a point and click that you can do that will show you at a given depth or at a given wavelength the different contribution as a function of height. So if you are interested, we can look at that. It's interesting because it shows what is important where and what kind of opacities you have. So there's a lot of things that indeed go on in the background that you never see any particular evidence for, but you have to collect all those the data for that and write the routines to do the proper calculations.
I want to ask a question actually.
Yeah, so just add that there is much older than our age. So we believe that not only much older, but also the assumptions are a bit different. So we believe that our age background opacities computations are more accurate. So in the case of this side, as I said yesterday, when we start, we run our age. When we finish the process, we also run our age. So every time that we run our age, we use also the same background opacities. So everything is consistent. So the computation done inside our age to get the populations is compatible with the last computation done in the side part using the same background opacities. And what Han was also saying, we are thinking about the possibility of also getting the tabular values for using maybe for SER as well. But in general, I think for LTE lines that we usually use for SER, it's more or less going to be the same. But as soon as you get higher, then RH is the one that probably is much more accurate. So then for this reason, both in RH and the side, we use the background opacities from RH.
Not quite sure how to formulate this question, but I'm skipping in front of Kai just because it's related to what you were saying. What kind of errors do you make when not solving hydrogen in non-LTE when you solve for other atoms in non-LTE? Because I'm assuming, I mean, you're talking about H minus, for instance. So if you don't solve
so for
hydrogen,
H minus, it doesn't make a big difference because H minus only has opacity at lower heights,
okay.
and it doesn't contribute much from temperature upwards, temperature minimum upwards. So there, the biggest error that you make is that you get, if you assume hydrogen in LTE, that you get the wrong electron density,
Yeah.
and the electrons are the ones that have the collision, make the collisions. So you have wrong estimates of the collisional rates.
Okay.
And that goes, so the line profiles typically are not very sensitive directly to the collisional rates. The collisional rates more or less determine where you thermalize a spectral line, so where it decouples from the local conditions. And so there is some influence, but it's not a very direct influence.
Can I add something before Kai? So it's some of kind of homework that I have in mind, that is doing the synthesis for calcium line, but including hydrogen as an active atom or not. And I think he believes that it will probably improve, but I need to do the test and compare embedding calcium data with hydrogen as an active or passive. In principle, for the code will be the same. Hydrogen atoms are relatively simple and stable. So if we see that it improves, then we will just use it as default. So now it's only calcium as an active, but I just need to switch active for hydrogen and it will work. And in principle, we guess that it will be better, but it's homework that we want to do for the future. But probably we should do it as a default. So solving hydrogen populations for at least the standard levels to get calcium right. Yeah, that is homework. I think you agree that probably will help.
Yes.
Yeah, we have a. I'll stay. That's right. There's a recent paper with Ryan Hoffman where he looked at the inversion with and without the hydrogen treated in non-LTE or non-LTE, and it increases the temperature basically that you get out if you include the non-LTE treatment of the hydrogen.
Yeah, because you compensate for the lack of collisional rates
Right.
if you have fewer electrons.
Right, so you can you get it right. And that agreed better with the simultaneous ALMA data, which indicated that it was a more realistic temperature, including the the non-equilibrium
Okay.
hydrogen.
Sorry.
I think I got the question. So maybe I can share the paper. So do you want that I share the paper and then we can look at the figure?
Compare the two, the top is the model and the bottom is the immersion. Both the immersion and the model show some variation from in the horizontal. But it seems like the desired immersion gave us some more stronger variation in the horizontal direction. So how much can we trust about that?
So you mean larger variation at these layers or here? Because here I think it's essentially matching that, right? But for example, here it doesn't match very well. So this is what you're asking for. So what I would say that in general, these and these, they are very close when you move between 0 and -5. But then as you go below 0, then you have that the match is not as good. And then here it's also not as good. But I guess this is because the spectral lines that we are using in this inversion, they are not sensitive between those layers. I mean, above 0 and above -5. But I would say that here the variations are the same, right? Except maybe some small fluctuations here, but this size and this, is it the same for you, or do you feel that this is not following the trend of the simulation?
Oh, it's okay. Yeah, but I think is this just from one line from the CASM2 line?
No. I think it's. I think we have a lot. So you have, I think, sodium, potassium, calcium, chromospheric and upper photospheric lines, and iron 613, 6302, and 6301. But there's still all those lines. They are essentially sensitive between 0 and -5. So above that, this fluctuation is because we don't have sensitivity. So the code is doing the temperature going high or down because we don't have sensitivity. But for me, these variations, they were very good. But you have to consider that these, so we have the same number of points in height scale, but we don't have the same resolution. So I mean, you have several lines here, but still you cannot solve each optical depth 0.1 with high accuracy because lines, they are sensitive to a given range of heights. So even if you have a high resolution in this way, in this simulation, then here is a bit smoother, simply because for having the same resolution, you would have like 100 lines or something like that. Because lines, they don't form in just a delta optical depth scale. They have several optical depths, like, I don't know, 0.3, 0.4. So then you get like a smooth behavior compared to this one. And if you're talking in the horizontal direction, so each pixel is treated independently. So this eye doesn't know anything about closer pixel in any direction. But for me, this result was indicating that it was very close to the spatial variation of the simulation, at least between 0 and -5. Do you feel the same or?
It's seems okay for me, but is it possible? I just made that it's possible to use the the nearby inverted model as the initial guides for the nearby pixels? Is it possible to improve the smoothness of the
So
nearby
definitely
pixel
you
feedings?
can do this, but this is if you know what you are going to get. I mean, if you are in the sun and you embed one pixel and you said, I think this is the atmosphere I should get from this pixel, I will use it as a starting point from the next one, then you are imposing one condition that in principle you don't know if you should impose. In the case of the simulation, you know what you need to get, but in the sun you don't know what you need to get. So you can do that. Definitely you can decide which inversion, which starting atmosphere you use. For example, you can run the inversion with a simple configuration for the full map and then use the results as a starting point and then run the inversion again. That's definitely possible. But I recommend you to just be careful with imposing preconditions because the code will struggle to move away from a solution that is relatively good. And then you are really just marking or defining the path where the code should go. But it can be done. Yeah. But just to confirm, do you believe that this spatial variation like this, is it bad? Do you think it's bad? Okay. Okay. I think this is the best picture, the results from for the paper, because it's really, the code doesn't know anything about the nearby pixels, and still you see a smooth variation in almost all the parameters. So we are a bit demanding. Han, do you want to add?
Yeah, no, I just with respect to using the previous solution, if you divide up the domain into different parts and you send it to different nodes and different CPUs, it's not obvious to me that you always have the solution that of the previous or the next door pixel or what that means. So I think it's hard to do consistently if you do a whole inversion in parallel on a big machine.
Yes.
But yeah, I mean, it's something to try.
Something that you can do, and something that we are already thinking about, is that you can, for example, compute, if you are using calcium, the weak field approximation for the full map is really fast and is reliable. And then you can start from the solution of the weak field approximation, the inversion, and then just let the code to have any number of nodes in magnetic field, but you're already starting from a relatively good solution. We believe that this probably will work and will help reducing, for example, the number of initial atmospheres that we need to use for getting smooth results. But in this case, you are still working pixel by pixel, and you're applying a method that we know that works for as a first level approximation. But I think using one pixel to decide how we start the other, it's delicate. So I personally don't like it, but you can try it, definitely. Yeah. Okay. So how about the others? Because I'm concerned now. I was really happy with these results. So if you see these, not offended, but just worried that for me was great. Because don't forget that this is really stark variations along the line of sight and along the spatial domain. So this is 48 kilometers spatial resolution. And in height is 20, I think. So we're talking about high spatial resolution and really stark variations. So getting this, it's hard. I promise that. Yes.
I have a question that, along this topic. So when you do the inversion pixel by pixel, which is vertical in this plot, and are the nodes in optical depth always the same for each pixel?
Yes. So the nodes are, for example, in this case, I think it was like 9 for temperature. The location of those nodes.
It's
and
always
the optical depth is, everything is the same.
All right.
So then let's see this way. So when I did the synthesis, I used an atmosphere with 81 points with a step of 0.1 optical depth. And when I did the inversion, I had 9 nodes. So then each node is separated like 0.3 or 0.5 in temperature, but then velocity was 5 nodes. So then you have nodes that are separated like every 0.7 optical depth scales. And then I think the azimuth was even lower. So then you're trying to reproduce an atmosphere with 81 points of 81 points with an atmosphere that was perturbed only in 9 positions or 5 positions in the case of velocity and magnetic field. So you will never really get these short scale variations in height because we don't have enough spectral lines to have like 80 nodes or 50 nodes. We will move probably between 5 and 9 unless you really add like 50 spectral lines covering the upper photosphere, the temperature minimum, and the chromosphere. But we don't have enough chromospheric lines to do that. So I think is that still it's good that someone tell me that this is not as good as I was thinking, but yeah.
Why does the sodium line not look like the actual sodium line on the sun?
I don't know. We have an atmosphere that I don't know how close to the sun is because this is the BIFRA simulation. And of course, the code can make something weird, but I would start thinking that the atmosphere can be less realistic than the sun. Yes, this is 1 pixel, just to show how the accuracy of a given pixel looks like for all the lines together. So it was like a demonstration of can we embed multiple LTE and non-LTE lines. So in this case, we have a magnesium atom as an active, potassium atom as an active, calcium 2 atom as an active, and sodium atom as an active, and then 2 iron lines as a passive, so in LTE. So we are solving all the problem, and it was stable, and the inversion was, for my impression, very good. But I think probably the atmosphere also, you can see how for this pixel, how the calcium 8542 line looks. So I think it's probably a complex pixel. Maybe we didn't have microturbulence probably in this case. So maybe the atmosphere is just a bit complex.
Compare, I would start to look at the average profile to see how it compares to the atlas, right? And I don't know, I don't think we've done that for sodium, so I have no idea how close it looks. But
yeah,
these are very high resolution spectra, right? That, as Carlos said, the grid spacing is 48 kilometers. So maybe these spectra look like that too. I don't know.
Yes, but also we have a lack of turbulence in the simulation, and I think in this case we didn't add a micro turbulence. But all the work that I have done with this simulation, at least for calcium, we need to add between 3 and something micro turbulence kilometers.
I mean,
So,
this is a model, right? And
yes,
Bifrost is famous for not having
yes, it's still
enough
broad
line in the chromosphere.
Yeah.
Why, I don't know.
Yeah, I think probably something is missing. Sometimes spatial resolution, they are going in this direction because they are thinking that, well, thinking and testing that as you go with higher spatial resolution, local scale, local scale turbulence motions started to appear, and then the broadening of the lines is larger. But this one is the starting first runs that they really were stable, but of course with limitation. Okay. So more questions? Shall I stop sharing, Mateus, or do you want?
Yeah,
leave it.
not about this.
Okay, good.
I just have a comment and a question. The comment was regarding the hydrogen non-LTE. It is usually better, the results, but depending on the atmosphere, I have done some tests, it doesn't converge well as considering in LTE. So sometimes you have to first consider in LTE, then you get to an initial solution, then you perturb that solution in order not to get stuck in that minimum, and then you start with non-LTE. Otherwise, the code, at least in my trials, gets lost for many pixels. Stick, yes. So I don't know if that happens with Desire too, but at least in my experience.
Yeah, it's the same problem. So, well, not problem, but is so both are based on RH as a forward modeling. And I've done, for example, tests with bifrost simulation, and the rate of convergence that you get with calcium too, it's almost 100%. But for example, if you move to hydrogen as a non-LTE atom, then you start having some pixels that are either too cool or either a bit complex, and then the code does not reach a good solution for the non-LTE problem just because of the hydrogen atom, but the calcium atom works. So I think, yes, for me, the homework is that it's not really testing that it improves, is that at the same time is stable, because the inversions that you see there, basically they didn't fail, but it's only with calcium. And my fear is that when we add hydrogen, we will improve a lot, or we will improve the pixels, some pixels, but we may also get convergence issues. And I need to think how we deal with that. So either, as you said, running once with LTE and then from there switch on, or the another way, maybe reducing the duration limit, so to make it easier for the hydrogen atom to reach good convergence. But this is my fear. I feel that calcium is really, really stable, but as you move to magnesium or sodium or potassium or hydrogen, then things become more tricky, at least with bifrost. And if you add PFD, like if you are trying to synthesize Lyman lines, then it's even more complex. So this is my fear, how much we lose in terms of convergence, respect of how much we gain for a better fit of calcium.
Yeah, and the question I had was about beta reduction. So in comparing sleet spectrographs and filter graphs, how do they compare when you have to take into account the wavefront calibration? Because reducing sleet beta is usually quick comparison to filter graphs, and with filter graphs you usually have to wait a week or 2 weeks later you get the data. And even when you try to do a image deconvolution, you get some fringes in the data. So I don't know if how does this affect what is the differences between the two instruments in that regard, at the quality of the ultimate quality of the data, because of the estimation of all the properties of the atmosphere before it gets to the telescope.
Yeah. Fringes, in fact, you have in both cases, but the idea is that in the 2D, you see them like this, like someone scratched the map, but in the spectrograph, you see them on wavelength. So if you take one raw data, for example, from Greece, you will see a lot of perturbations. And you will have them, but it's just that you see them differently. So you will have, in both cases, always fringes. So I think it's just that in 2D imaging, you see them clearly, but in the spectrograph, you also have them. You sometimes use like a cosine or sine function to reproduce some of them, but still they are a combination of different optical elements, and it's not always easy. But now, Kevin, probably.
Yeah, I mean, obviously, yeah, the fringes, they're always fringes. The image reconstruction process for the filter graph data is another computationally expensive thing, right? So it's another least squares fitting process to recover the PSF and then apply the deconvolution. So yeah, I mean, it requires a lot of that pre-processing that you mentioned, a couple of weeks to even get to the data that then you want to invert. And you have a lot more pixels, right? I mean, in a single filter graph scan, you have, on order 1 million pixels, right? Whereas along the slit, you have just whatever, 1,000 or 2,000 along the slit, a lot more spectral pixels. So, then the inversion process is going to take longer as well, just for the number of pixels. Yeah, and then you mentioned the non-LTE with the hydrogen. Treating that increases the time scale about a factor of 10 or so to actually invert a single pixel, and just becomes almost at this point prohibitive inverting large data sets, including that effect. So
yeah,
just So my impression, and I've always used in spectrograph, I never embedded imaging data. I think in both cases, we know more or less the effects that we need to check. For example, in the imaging instruments, you have the cavity errors that you know that they are there. You can model them with somehow with accuracy. And as month, if you apply the spatial deconvolution, thing like that, still takes a lot of time, but usually works. The only thing that I usually have in mind when I want to choose between one or the other is that usually it's very difficult to reach high signal to noise ratio with imaging instruments. So if you are thinking on really look at the inner part of the spectral line, then spectrograph is much better. But at the same time, if you are looking about dynamics and high spatial resolution, then you cannot do that with a spectrograph, because first, if you are scanning, you are losing the spatial resolution because you are integrating variously position. What else? And I said spatial resolution and time cadence. So if you spend 2 hours in one map, then and you're trying to look for chromospheric features that evolve in a scale of seconds, then you are just like taking a picture of someone running. You will see it, but it will be like with effect behind. So I would say that in terms of calibrations, both have issues, but both we have worked on them for a long time. So we more or less managed to solve them somehow. And I think it's mainly the topic that you want to address. What will be the reason for deciding between one or the other? But I think both behave well in the sense that we know more or less how to calibrate all the possible issues. And eventually we will reach the integral field unit period where we will have both. We will have 2D and then the spectral integrity, but it will take some time. So for now, it's just, for example, in your case, if you want to have fast evolving phenomena of limb, then you need probably 2D, even if you have a limitation in terms of signal to noise and nothing like that. But it's going to be challenging to put the slit on top of something that is of limb. But you will not reach time to the -4 in polarimetry sensitivity. So it's just, for now, we need to decide between one or the other and live with the limitation.
Or you won't get the dynamics at 10 to the -4. You could probably get to 10 to the -4, but then you would lose the dynamical information.
And the spatial resolution. Those things move.
Yes. And you were.
No, yeah, I was just wanted to add that you have to pick your poison, right? Because if you use the slit spectrograph, your spectral resolution, but also your spatial resolution, don't forget that depends on your slit width. If you want to have enough spectropolarimetric sensitivity and you widen your slit a little bit, you lose spatial resolution. If you have a filtergraph, you do not have simultaneous, there's no guaranteed integrity of the spectral line profile, because you take different part of the spectrum at different times. And if the scene changes, or even if your AO is not perfect and your image moves a little bit, you introduce false signals because you change one part of the profile, not the other part. In addition, we haven't even talked about at the high resolution that you have at Deakest, for instance, you have to worry about differential refraction, where the different wavelengths are refracted by the Earth atmosphere differently, and therefore are imaged on your instrument in different places. And if you have a shift by this refraction difference that is not parallel to your slit, then again, you don't have simultaneous wavelength information spectra. So there's always poison there.
But did you understand the last part? So it's just that if you put a slit like a 500 nanometers, put the same slit or just feeding the same light at 800 nanometers, you're not seeing the same solar region. That's because the light's affected by the Earth's atmosphere. So if you want to do multi-channel observations with a long slit spectrograph, you need to at least scan a given region, and knowing that part of the region will be lost because you will not have the for example, 3 channels, imagine 800, 500, and 400, they will fall at different locations in the sun. But if you have enough large field of view, then you will at least fit like, I don't know, 60% or 70% of the field of view. But if you just said, I want to have a slit and stare observation, then you will struggle to see the same solar feature.
I've told some of you already, but one of the existential observations, observational experiences was observing at the McMartin on Kitt Peak, looking at the CO lines at 4.7 microns, and it was fairly late in the day, and we were observing, and I was looking at the spectra. We were observing a sunspot, and I was looking at the spectra, the CO spectra, and it clearly showed the dark band in the spectra, indicating that indeed our slit crossing the sunspot umbra. And I was looking at the reflection of the light on the slit jaw, because that was clearly visible, and the sunspot was not on the slit. Because in the visible it was not, but in the infrared it was. But that's how strong that differential refraction can be.
You were 4 microns.
Yeah. Of course, this was an extreme case, but it was something that that strikes you as very strange.
So I heard a couple instrumental things recently that you now maybe will appreciate. So the Phi instrument on Solar Orbiter is a magnetograph that is a filter magnetograph, uses a Fabric Pro and scans through the 6173 line, the same one in HMI, and measures the magnetic field. So we talked about the seeing induced problems, that as you're modulating and the seeing is moving the image, you get crosstalk and it adds noise to your data. Phi, of course, doesn't have any seeing, but there's image motion in the spacecraft as they cycle through. The spacecraft pointing jitters a little bit and moves around. They have an image stabilization system that was supposed to be able to stabilize the image so they wouldn't have this problem, right? It would track the features on the sun and hold the image stable. As of right now, they can't really run that during the observation, so they have to turn it off, so they get this image motion. And now they have the problem that they have image motion during their modulation sequence that increases the signal to noise. And so they have to deal with that by downloading most of the raw data.
The noise to signal.
The noise to signal, right. The noise to signal. Yeah. So even in space, you have these problems of modulation. And the other one was then when they first started looking at their data, they were getting all kinds of strange signals in their demodulated data after they had corrected for the Mueller matrix of the instrument. And it turns out somewhere along the line, there had been some sign flips in there when they had calculated the instrumental, that X instrument matrix, and they had the crosstalks the wrong way. And so they weren't doing it. So they had to go back and correct that. But those sign errors creep in all the time.
And also it's difficult in space to keep them. In the case of Fabric Pro instruments, sorry. So in the case of imaging instruments, you define this very narrow wavelength region, and this is where you tune, and this is where you get to the information for this specific spectral region. But this is usually associated to the instrument working at a given temperature. So if your temperature is not stable, the region that you're defining will change as well. So if you are scanning along the line, but the regions that you are scanning are changing with time, then things become much more complicated. So in the ground, having things thermally stable is usually easier, but in space or in a balloon, this can also be another problem. So because the temperature is not making things wrong, it's just shifting things. And usually you don't model your instrument working at different temperatures during the operation. And then this means that reducing the data is a headache. So, yeah. Yes. Okay, so, but before going, this is not new. I mean, we always had in the past calibration issues and we have been solving it. So I think it's still good if you try to analyze observations. Don't get discouraged. It's just that you expect things to work in some way, and then sometimes minor things happen that you didn't expect, and then you just need to get along with them and solve them. But at the end, most of the observations, as I always said, they have some uncertainty, but still you can trust somehow, and you can get the information from there. Okay, so then if you remember, we were in tutorial 5, and I said, please copy these files here. And did everyone get there? So then I will just run. Remember that in the case of SEP, we loaded. This is the atmosphere we use for the synthesis. This is the atmosphere we used for starting inversion. I did 2 cycles, so then it's initial -2, and then this file should be there. So I leave it as a comment because hopefully soon I will just send you an email saying, okay, now the code is running the error file, but in our case, for this tutorial, it's not written on disk. So for now, just let's go ahead. And then I also change a bit the plot because in the SER plot, I was using this error bar. But now, as we don't have any errors, I just made a simple plot. Okay. So then if you let it run until 107. So let's see, where am I? So I go to tutorial 5. Okay. And then this is what I'm getting. Okay. So I think if you don't see it well, then I can. It's fine. Can you see it well? If not, I just plot the EPS. So now you will run yours, but let's focus on this one for a second. So remember that the fits were relatively good. Some small differences in stocks I, and then also a bit in stocks Q and U and V, but in general, they were good. And what we are getting here is that we started from the dashed line, and with 5 nodes, the code is essentially tracking the black line very well until here. Then here it starts to deviate, because in principle, calcium, you cannot never know exactly where it forms, but around -5, sometimes -5.5 is probably the limit. Beyond that, usually we don't have sensitivity. So then it makes sense that the code is trying to do something here, but it's not fitting the atmosphere. Or if it does it, it's just by luck. There's no sensitivity here. And also the same here about so below 0, then it starts to deviate because it simply cannot decide which temperature value should use. But it's getting very close in general, and even here. I was not expecting this one, and maybe when you show your results, we will not see very close relation here because the response functions, as you will see later, they are a bit low in around -4. Then they are a bit higher after that. So above and below that, they are a bit higher, but sometimes around -4, -4.2, we don't have too much sensitivity with this configuration. Then microturbulence is not doing it well, but I think that's fine because line of sight velocity is really good. And then I think probably these small errors here in microturbulence are also appearing here in magnetic field, and probably we have also some residual from not fitting the temperature perfectly, but still the error that we have here is really small. And then again here with inclination, instead of putting it flat, it's put in a straight line, and it's just crossing probably the region where the photospheric lines are sensitive and the atmospheric line sensitive is getting close to those to the initial solution in those regions, and then azimuth is fine. So, but just of luck because it can be also -100 degree respect this one. But in general, the results are very good. Temperature for me is always surprising to see that with 5 nodes, it moves from this one this one. So this is always good, but this is easy. So I would like to check your atmosphere with gradients and another atmospheric stratifications to see if the code is also doing well, or we are getting far from your initial solution. So does anyone want to show? Yeah, Vincent. Yeah, let me stop sharing. Okay, so similar as before, very good in general in temperature. We are seeing this deviation that I was mentioning, so I think we will see it even more later. But in general, then it gets closer again here. So the line core of calcium 9 is mostly sensitive in this region. Then here it's not so sensitive, and then here we have sensitivity from the calcium 9, but also from the photospheric lines. So I would say that this is great. Again, this for me would be like perfect. And then here again also seems very good. We start to deviate from here. So maybe for this reason, Stokes B is not exactly perfectly fit, but still these are small errors. And then here it's great. So for me, this is very good. How about 1.5 micron? Do we have conversions? Yeah. Yeah, so I think if we go back to the atmosphere, can we go back? So you can see there are some deviations here. So probably if we get it just on top, then we would probably fit this. So I would say that you are getting the amplitude right because we are getting close to these values around here. But then these small perturbations are probably because we are failing a bit here and also here in the inclination. You can see that we are not exactly on top. But yeah, this is what was going to happen in general, that maybe some small parts will not get perfectly fit, and then you are not really matching 100% the atmosphere. But the general tendency, we are going to get it. So then I would say that if you are doing inversions of observations, and you get it more or less well fit, then you should trust more or less in average what you are getting. And again, here you can see that in this case, it tried to put it a bit hotter, but then it was getting too hot, so then made it cooler, and then finally it get it right here. Okay, so this sometimes happens. So the code will change nodes and then will interpolate between them. And if it's getting in the wrong direction regarding what is needed in the next node, it will probably compensate like this way. So hotter, cooler, and then at the end, it got it right. Okay. Okay. So last person that wants to show. Yeah, Nelly. Yeah. Okay. Yeah. Again, we are close in temperature, but it seems here it was not so good. So in your case, the Stokes I is good, or is more or less the inversion of Stokes I? Okay, okay. So then it's probably because of this difference here, but still here it's getting close. So I would say that it's probably fine. Again, it seems that microtubulant is not getting it, but probably because there's always, I forgot about that. So if you get a profile and you change microturbulence a given amount in a given height, you can reproduce the same spectral change, that change in temperature a given amount in a different height in a Stokes I. So sometimes the code will decide to change temperature, and maybe here it's putting it a bit hotter. So then it says, then I cannot put the microturbulent as low, and then it's making it a bit higher to compensate the changes of temperature. So this is some kind of degeneracy that we will have. In general, it's not too strong, but you should be aware that the profiles can change in the same way, changing different atmospheric parameters. So the code will try to always get it as best as possible, but sometimes it will get confused and will change microtubule instead of temperature, or temperature instead of magnetic field. But this is, yeah, what it is. Okay, but the rest I think is fine. So maybe not so good in inclination, but still very close to 45. So I think it's fine. Yeah, thank you. Okay, so then any question before I move? Yeah, okay, yeah. Yes. No, I said that in principle it should be written on disk, but I don't know why. So I think there's probably some bug in the code that is not writing it now. So I will go Basilio and we will fix it. But so far it's not there because I don't know what is. So it should be there, but the code is not writing it on disk now. So it's a bug that we need to solve. Okay. If you want to get an estimation in the meantime, we can compute the response function. That is the next tutorial. And you can just by hand compute the inverse of the response function and then plot it on top of the atmosphere. Because you will have the response function, it's covering the same optical depth. So then you can take the maximum value of the response function for the 4 Stokes parameters. So imagine you take optical depth. Well, let's go to the response function and then I will tell you. But in principle, you can do it manually in a similar way as Desire and SER does it. You will not get exactly the same amplitude because Desire also adds weights and additional elements for weighting the response function, and then the certainty. But then we can at least get an estimation of if you don't have any sensitivity at all, or you have much more sensitivity compared to the weights. I will show you the response function, and then based on that, I will just give you a hint of how you can do it. But eventually, we will have the errors on disk. Okay. So any other questions before I move? No. Okay. So then I will share my screen. Then we go to tutorial 6. Then we close here. And then here we have, again, that we need to copy these files. This is easy. So it will be the atmosphere that you got in the final cycle. So if you run it 3, 4, then just copy this one. And then the profile, you can pick any. It's just to get the information of the wavelength range. It's not contained in the response function file, but you can get it for example, for this one or the last one. And then we just run in the same way as we did with SER. So I will just put a stop here. And then if you remember what we did, so in this case, I copied all the files that we used in tutorial 4. So the same input, abundance, wave grid, lines, everything. And then just put 1 in Stokes IQ, U, and V, just to keep things consistent. And then -1 in the number of cycles. Okay, because we want to compute the response function. So then -1 there, 1 for all the Stokes parameters. And then if you remember, here when we are in response function, let's say mode, 1 means compute the response function, blank or 0 means don't compute the response function. So then in this case, we are computing the response function for temperature, magnetic field, line of sight velocity. Okay, these 3. Are you following? Yeah. Okay. So then I will run the code just until this stop in line 60, just to check that it's right in the response functions. it's running now. And then you see that it's running, it's writing the response function to electron pressure. I don't remember why it's doing this. I think I remember Basilio telling me that it will do it. I don't remember why, but still let's focus on the ones that we are going to analyze. And it will be temperature, field strength, and line of sight velocity. Okay. So can you try to reach this point with your atmosphere just to and your configuration file? Sorry. Then you need also to put the wave grid file inside input. I forgot to put that. So you need also here to copy. Put. Okay. So then can you try it? Did it work? Yeah. Okay, so then the next step, I'm going to do it first and then you can do it later, but just comment this line because the response functions, they take some time. So just comment it. We don't want to compute it again. And then what I'm going to do is to read the response function, okay, for temperature. And then in this case, remember that we are using the function read response function because we are using magnetic field. But if you have a magnetic field that is 0, then you need to use another function inside the Python script that it will be read rfi, I think is the name. So we are going to read the response function and I'm going to stop here. Okay. So this will be dot here. And this is the one that you get. I'm going to use the PS because it's much better. But this is the same plot that I got. And then we will try to run your case. So the important thing here is that I'm not changing anything. So if you remember when I plotted the profiles at the beginning, we said, well, it's not correct because first this part is longer wavelength than the other. So we need to flip this and they are not continuous. But in this case, I wanted to start from here because I wanted to show you how the response functions really differ between photospheric and chromospheric lines. So you can see that they tend to have the same shape like a Gaussian, but it's the height where they reach what is really different. So I said this one reach higher than this one, but essentially they are around -2.5, maybe -3 in some cases. But then calcium goes here. Okay. So then if you do the inversion with these two lines, this is probably the wavelength range that you are covering for temperature. But now if you add this line, then you already have it until this point. Okay. But at the same time, you see that here, as I said, you have strong sensitivity here, but then it's very low around this region, and then it gets really dark again in the top. And this is because how the line is. So in general, combining these two, we will get a good high resolution from log tau -0, 0 point something, and then it will start to decrease. And then here we will have like some kind of lag information, and then we will get information in the upper part. Okay, but the important thing is that if you compare them, this one reach much lower than this one. Okay, and now the next step that I did was, okay, I'm going to split in two, and then I'm going to also write horizontal bars, so then you can see a proper comparison, and it's this one. Okay. So if everything was correct when I did it, so now we have that they are in the correct wavelength. This is 6301, this is 8542. They are in the correct scale. So this is around lockdown 0, and then around lockdown -3, it's getting weak. And then this one bridges -5, -5.5. Then I think this is a good comparison between them. So you can see also that colors are important. So in the case of each panel is normalized to the maximum of the response function included in the panel, just to keep things simple. So then one is from the continuum, and then the sensitivity is a bit lower here. But then in the calcium line, the part of the response function with largest amplitude is coming from here. The line is very sensitive to temperature changes in this part. And the wings are sensitive as well, but with less sensitivity. Okay. So did you follow this part? Yeah. Okay. Can I see yours? At least if this one, maybe it will not work because you need to change the scales and things like that, but probably the first one, this one, probably will work because I didn't add any conditions, so just put all the profiles together. So can you try to run it until the 137, just to see your response functions to temperature? Okay, you got it, Lenny? Yeah, okay, can I see? Okay, so I don't know, probably the scaling. It's difficult to know what is happening here. Definitely here we have much larger amplitude than here. So for this reason, this is basically gray and this is really dark. So I don't know if there's some numerical issue, because I'm also seeing here some different things. So I would need to check with you, but in principle, it's showing essentially what we said, that in the case of calcium, this part is going to be the largest contributor to this sensitivity to the temperature, although it's fine because this is the line core. So it's saying the line core is very sensitive, but in these layers. Then the wings are less sensitive to temperature, but at these layers. So in general, the line is sensitive to all layers. It's just that the core sees changes that happens at higher layers, and the wings see changes that happen at lower layers. There's no degeneracy, but this is good. And in your case, you have a strong magnetic field, and for this reason, we see these strange patterns here, right? Okay, thank you. So how about Nancy? Do you get it? You okay? Okay, so then that's, yeah, Vincent, yeah. Good, good. So then again, similar as before. So I think in this case, things are more reasonable. So then strong contribution here, strong contribution here to changes in temperature. And then here is still strong, but weaker than here. But again, it's fine. The problem is if you have a spectral line, you want to analyze, you compute the response functions, and you see, for example, like this, but then you see also strong contribution here, and things are complicated because it means that when you change the temperature at this optical depth, the line core changes, but also when you change the temperature at this optical depth, the line core changes. So then when you're solving for example, the inversion problem, the code will not be able to decide if it needs to change the temperature lower layers or higher layers. But this line is one of the smoothest one in that sense. So you see very, very, very smooth, then jump, but still here is also very smooth, at least for temperature. So I think this combination is one of the best combinations you can have. And in fact, it's the one offered with WISP, at least in the first call. And I think also in the second call is offered. So, thank you. So, yeah. Oh, okay. Yes, good. Good. I think she goes first and then you go inside. Yeah. Okay. Good. So I think that's nice. So do you have strong field, strong magnetic field? Yeah. Okay, because you can see that now the strong contribution is a bit lower. So sometimes if you have a strong magnetic field that can affect the height of formation, it can shift the height of sensitivity is a bit lower. So I think for this reason, it's not reaching as high as the one that I showed. But still, it looks fine as before. And then here we see the splitting of the Zeeman effect. But again, strong color here, strong dark color here, and then smaller, so weaker color, but smooth in general. Okay, good, thank you. So then, let's do one thing. I will move to velocity, so to line of sight velocity response functions, and then you can show it to us. Oh, okay, you're already doing it. Okay, yeah, it's fine. It's fine. It's fine. No, no, it's fine. It's fine. I think here it's very nice because no, it's good. Yes, yes, yes. So you have strong gradients along the line of sight in line of sight velocity, and then I think these just change a bit how the response function looks. Usually tend to be bended towards where you have the gradient, but it's sometimes I don't understand it. But in general, when you see this behavior is that you have velocities, but also velocities that change with height. So then it's going this way. Sometimes I just think that it's beautiful, but I don't understand it. But still, for me, the thing that you need to always double check is it's always smooth, or you see like double peaks at the same wavelength but different heights. If you see peaks at the same wavelength, so this is same x-axis, but at different heights, then it can get complicated. But if you see like this, but still is always increasing with height but moving to different wavelength, then it's fine. But this is gradients, the effect of gradients. Okay, good. So then what I was going to say, so then let's move to the next part, that is the response functions. Stokes I response functions, but respect to already done. And then we enter in response functions to line of sight velocity. And this is Stokes I again. And I will just put a stop here. How it goes. Okay. So then I will open APS. So it looks a bit better. And then here, still relatively simple, but a bit more complicated. And you saw this with hand this morning. So in this case, it looks fine. So it means that the Stokes I profile, we change in the opposite direction when you are changing the velocity. And this is because if you apply a constant Doppler shift, for example, to the red, this part will be more positive, but this will be more negative respect to the line center. And if you do it in the other way, it will be an opposite behavior. So this gets closer to the wave, to the line core, and this gets farther from the line core. So then you see this opposite behavior, but in general symmetric. But so if you check your zoom, there's a shadow here. Can you check your zoom, because, or just open the figure? So I try to really push the saturation here. So this is already saturated, but it was just to show you that there's a shadow there. And the idea is that, again, the calcium line is extremely sensitive to the changes in line of sight velocity, but in the line core at higher layers. But there's some sensitivity in the wings, but the line is so broad that you basically will not get too much from that. So only inverting calcium line, you can try to at least put nodes in line of sight velocity and try to get some information from lower layers, but it's very limited. In general, it's better to combine it with a photospheric line because sensitivity to velocity is very weak. For this reason, I really saturated the plot to just see the shadow. And in fact, the projector decided that it would not show it here on the screen. So it's there, but very, very weak. So you need always to complement this line with this line if you're planning to get line of sight velocities, simply because it's really, really broad. Okay. I mean, line of sight velocities at lower layers. Here it will be very sensitive. Okay, so who had strong line of sight velocity gradients? Definitely SIDA had, but does anyone want to share the screen, or shall we try SIDA again? Nancy, yeah, okay. No, okay, okay. SIDA, did you get it? Okay. No. Yeah. Who is? This is Nancy. Okay. Okay. Yeah. Okay. Yeah. Okay. So then I think the quality of the projector is probably a bit. So here we are probably a bit demanding for the projector we have. So maybe there's some shadow here, but it's not so clear. But still, the important thing is that when you get gradients, it becomes really like challenging to see what is happening. But again, this is like not at exactly the same wavelength. So again, we can get some information of the gradients around here. And then if we combine it with this response function, we will get probably a good estimation of velocities. But I think in your case, when you compared atmospheres, they were close, right? The velocities. And then when you see this, it's because with a complex atmosphere, when you change this optical depth, yeah, it changed in a way that is sometimes difficult. But still, I think it's fine. And then I was going to say something. And yes, and we will see it later, I think, in response functions to the magnetic field. But sometimes you can see that this is blue, and then it gets red here. And if these were more or less symmetric, sometimes you can get blue here and then red here. So in terms of positive and negative, so you can get sometimes a negative change here and then a positive one here and the opposite. We will see this in Stokes P, or sometimes you can see it, and is that Stokes P signals, they go, for example, positive, Stokes P, positive and negative, and then suddenly it just does the opposite. And this is because mainly the reason is that the temperature in the photosphere is going down, 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 down. You read the temperature minimum, and then it starts to go up, up, up. So the calcium core is in the upper, in the part that is going up, and the wings are in the part that is going down. So the temperature gradient is different between the core and the wings, and sometimes you just get the opposite response to the same perturbation. Okay. Just in case if you see this change of colors in your response functions, is mainly that. So you're seeing a decrease in temperature in the wings, and then an increase in temperature in the core. That also affects the source function. Okay. Then let's go to Stokes P. So if you let it continue running, until line. So we are now reading response function to the field strength. And remember that in general, Stokes B is the dominant component. So we are plotting Stokes B response functions normalized to the maximum of the Stokes B response function. This will be until 285. Okay, so we close this one, and then I go to the EPS file. And then here again, yes, so please check the zoom or just open the EPS file, because then you will see that there's a shadow here. Those be signals. And this is again, I'm saturating this just to check this one. You can do a test. You can later on take, this is a 2D array, but you can make a normal plot, 1D plot, and plot, for example, the response function at this wavelength, this wavelength, this wavelength, and then at this one. And you will see that in the wings, it will be high in the, for example, for temperature, it will be large in lower layers, and then it will go down. Well, sorry, I prepared it yesterday for you. So in publications, I put this paper. You can check it. This is only for calcium 9, but this is what I was trying to set now. So in this case, gray color will be gray color here. So response functions to changes in temperature, for example, Stokes I, response function to changes in temperature. In gray will be this part. Then purple will be this part, and orange is the line core. So then, for example, for temperature, the wings are sensitive, but then they drop. And then when you get close to the core is where you start getting these response functions. And then as you get closer to the core, they will peak here. And then the one in this orange, that is exactly 0, will be the one peaking around here. And also they have this behavior, but this is just because they are complex. But essentially, different wavelengths, they will have a peak in sensitivity at different optical depth. Okay, this is just calcium. And for example, with the magnetic field, you have this. This is what I wanted to show. So you have a given amplitude, and then you have small thing here, and then essentially nothing below, because it's really, really weak how the wings, as those big signals change when you change the magnetic field in the wings, because the line is broad. So it basically no sensitivity. So in other words, if you are trying to estimate field strength or the field inclination at lower layers, need an additional photospheric line like these ones. Otherwise, with calcium only, you will not get enough sensitivity, simply because there's no sensitivity when you compute response function. Then it's always good to have coordinated observation of multi-wavelength observations with calcium if you want to get high, and then any photospheric line. It could be a weaker one, but it still will give a lot of information compared to calcium. But if you can get 6173, 6301, 602, 1.5 micron, 5250, then you're getting the best option. But any photospheric line with a given sensitivity to the photospheric field will help a lot, because the calcium is not sensitive to those layers. Okay. So did someone had a magnetic field with gradients? Lucian, can you share with us? Yeah, when you're ready. Yes, let us know. changes in the Stokes V response functions to changes on field strength. Okay, and this is 1.5 micron. Good. So then here, for example, it's even a bit complex. So it's red, then some blue here, and then red again. So very interesting. So you have a gradient large, so with bigger slope, or okay. And this line is completely split. So good. Sometimes if you have strong electric field or strong, so if the parameter that you are trying to compute the response functions to is strong, sometimes you can get like some ghost, right? I would say that in general, we are not so sensitive to this. So sometimes you can have it, but it may be some numerical error, because sensitivity to the magnetic field, it depends. This line is 1.5 microns, so maybe you are getting there, but with 601 or 50-50, it's difficult to get to 0, because the magnetic field usually peaks around -1, -1.5, and after that it drops very quickly. Velocity, more or less the same, and temperature, yes, temperature you can go a bit lower because of the continuum. But as this is mainly due to the central part of the line, then you are not usually getting sensitivity at locked-out 0. But if you see this, it may be because of the model that is complex, or it may be some kind of numerical error, and just don't pay too much attention to it. Okay, thank you. So then let's see what I have. Okay, so I think it's time to make a break. We have done the main part. Again, I have prepared tutorial 1B and 4B. These are Bifrost, so the ones that we had in the paper, 2 pixels, very complex pixels that if you want, and if you have time, we can do the same. So we do the synthesis, we do the inversion, just to give you a hint. So we are talking about profiles that, sorry, I want atmosphere. We are talking about profiles like this. So the black is original, and this is 1 pixel, and then we will have a second pixel. Will be this one, and then, sorry, this is figures. And something like this, that you can see that we are getting in a very complex territory. So we can do this again. It will be fast because the synthesis, we may even skip it because I just put the atmospheres and it's just running the code, but we can do it depending on the time that we have. And then we do the inversions. And then I also prepared this morning very quickly one example in tutorial 1C, where I'm going to help you to add to the lines file, to the atoms file, the wave grid, another non-LTE atom, sodium D line. So I can help you more or less to give you the steps that I will do, which database I usually go to check things. So we can decide if we want to do both things, one of those things, or none of them. So after the break, let's discuss it, because I would like to talk a bit about things after the workshop that we can do together. I'm leaving tomorrow morning, so today is my last day. So depending on how this evolves, maybe we can do tutorial 1C, that is adding a new atom and introducing non-LTE spectral lines in the grid file and in the lines file, so you can get a feeling of how this is done usually, and then we can leave tutorial 1B and 4B as a homework, because it is essentially doing the same, but just with a much more complex atmosphere. So after the break, we decide what you would like to do, and I would like to finish earlier today. It's been a week and a long weekend for everyone, so I don't want to push until the end because I know that we have progressed a lot. So I'm really happy of how things are going. So for me, finishing 1 hour earlier today is perfect. Okay, so then let's discuss after the break. Yeah, I think it's fine. Yeah. So, are you ready? So before going ahead, Dushan asked me a question that I then realized that I should have explained before, but I was just going a bit fast. So I think most of you are getting the correct in the sense of shape response function, but it's not exactly the real one in terms of number of optical depth points. So what is happening is that if you go to the place, I will go, but then later you can check. So we have codes, and then we have design inside, and then we have source, and then we have this file. I will go slowly, or then I will repeat it. I want to show what this file. So when you compile the code, you assign a set of values for different variables that we will use. This is all Fortran 77 stuff, so just is what it is. And the idea is that we are now assigning, in your case, it will be here 20, if I'm not wrong. So then the code is saying I will be able to use a maximum of 20 nodes. In the case of computing the response functions, they are always only computed in the location of the nodes and then interpolated. So then the response functions that you are getting, they have dimension 20 in optical depth, even if your atmosphere is 81, because it's just doing an interpolation, but they don't look as they should look. The ones I have, I changed this here, and now it's 200, so then I will get the correct one. So then let's do this exercise. So you go to where you have your code. Imagine that is in this case, codes. And you open the side where you're running the code. And then you go to the folder source, okay? Or SRC. And then inside, you will have a file called parameter. Where it is? No, I don't. This one. Just probably is without extensions. You may need to tell Mac that you trust this file. It's not a dangerous thing. And then you open it, and then you will have 20. Do you have 20 in KM? Okay. So again, for the inversions, usually 20 is fine because using more than 20 nodes, I think it's not going to be normal, or you may not do it never. But if you want to compute the response function completely, so with the dimension of the atmosphere, then we need to change this here. And the idea is 20, it has to use a lot of nodes and go faster. If you put 200, like I do, it's fine. I think the difference in the speed is not so high, but as we are thinking on multi-line inversion of very big maps, we are trying to optimize everywhere we can. So then for this exercise, let's change this value, and then you need to compile again the code. So then you need to go through a terminal to this folder source, and then you need to type make space fc equal gfortran, and then space install. Shall I say it again? Yeah. So let's open a new terminal. Then I go to codes, then decide. Are you following? Yeah, decide, then source. Okay. And then after changing the parameter file, then we need to type make fc gfortran. I assume everyone has gfortran as a compiler for C and for Fortran. and then install. Okay. And then just enter. And then the only thing that the code will do is just change then the number of points assigned to that variable. Okay. And then when, yeah.
I just have a quick question. So is Kn the total number of nodes allowed across all variables, or is it per variable?
For each variable, you will have 20.
Okay.
Yes. Yes. Thank you. Yeah. Good question. I think it's 20 for each variable, but let me take note of that. Okay. Oh, yes, let me close the node. I would say that is 20 per atmospheric parameters because we are computing at the same time response function to temperature, magnetic field, and ionospheric velocity, and it's not complaining. I think if we try to compute all the response functions, eventually we will get error from, I think, KT. No, not KT. I think KLD. So I think if it's working for 2 or 3 response functions, I think it's fine. So it's 20 nodes per atmospheric parameter, but I put a note. So when I will go home, I will sit with Basilio and I will check it. But I will say, as the response function is working, computing more than one, I think it's 20 per atmospheric parameter. Then you can have 5 in temperature, 5 in velocity, 5 in magnetic field, 5 in inclination, 5 in microturbulence, and so on, and should work. But I will double check. Okay, so now can you repeat the computation in tutorial 6 and check if your response function looks a bit smoother? And also if it has 81 times something, 200 or 800 working points, 201, I think. So Dushan, in your case, does it now look better? Okay. Cool. So then if it worked, then now probably you will get a smoother response function with the right dimensions. And now it's up to you if you want to go back and recompile or leave it like it is. In my case, I think the impact is not so high, so I leave it like that. But by default, I think every time we release a new version, probably this KN will be 20. That's because it's faster. But just be aware that if you get some of these issues, then usually the place where you need to update the values is here in parameter. Okay. So then we close these, and then we go back here. Then what do you prefer to do? I think probably it will take 30 minutes to do any of the options. So to go to more complex pixels, to embed them and play a bit, or to try to do something new, that is try to more or less get information for a new spectral line, to check the atom and to make everything work, and let's just run the synthesis. So what do you prefer, something new or just a complex atmosphere? Okay, let's do something new. And just before something new, I will just point you to In tutorial 4B, if you go until the end, here, sorry, this is the last plot. Yeah, here. So weights part 2. So it will just briefly introduce how you can compute create wave-independent weights. And I will just leave it here because I think it's really tricky to make them work, but at least just to show you how you can do it. And if you want to add it at some point, just let me remove the stop just to have things with the right contrast. So then, sorry, it's comment this one and this one, and then to comment this one. And then you can run it at home. It should work. And if you add different lines, you can compute a different profile in tutorial 1B that we will add noise in the same script. So it will just end with the profile that you need to copy here. And then you can just run it here with the same atmosphere. Okay, so then the idea is that for wavelength-dependent weights, we can create a file like the profile file. So like this. So it's the same. Index is the first column, wavelength is the second column, and then we have the 4 Stokes parameters. Okay. But then the values that we add in each wavelength here are weights. Okay. So then when I was preparing this one, I said, okay, I think the line core of calcium 8542 is the region that I need to fit well for get the chromospheric magnetic field. So then I assume that the line core was starting approximately around minus 300 milliampere. So then I just put it 5 for all the Stokes profiles until here. Okay. So I'm just creating a profiles file that is 1 for the Stokes parameters, except in the line core region of calcium where I'm putting 5. So then what I'm telling the code here is, okay, when you compute the chi-square as the difference between the observed profile and the synthetic one, the wavelengths of the line core of the calcium, they weight a bit more. So the errors in these wavelength regions are more important for the computation of the chi-square. So then the code will try harder to embed this region than the other ones. Okay. And this is a multiplicative factor with the ones that we have in the control file. So in the control file, if you have the Stokes I, Q, U, and B weight differently, they multiply with this one. They don't replace each other. So they just add on top of each other. Okay. So if you put, for example, here 10, and then you have another 10 in the control file, then you are multiplying a lot. So just try to put here, for example, the same number, and then modulate the ratio between Stokes I, Q, U, and V through the control file. Okay, so here is where you modulate how much Stokes I, Q, U, and V weight between each other. And then in terms of wavelength, just use the same value in the wavelength region that you are interested in using. Okay, so then very simple. If you want to play in the last part of the program, I just read the profile, and then I just multiply it by 0 and put 1. So then all the profile is 1. And then just for the wavelength region of the calcium 8542 line core, I added, in this case is 2 because I was playing, but in the other case was 5. So then 1 for everything, and then 5 or 2 for the region that you want to weight more. Are you following, Aidan? Should I try again? It's just that what we were saying before. So now the calcium line core is very, very sensitive in the upper part of the atmosphere. But yesterday we saw that the amplitude of the stock signals, it was always much weaker than the iron lines. So then the code, if it's just comparing them together, it will say, okay, differences or errors in the Stokes-B amplitude of calcium are less important than the errors on the iron line because they are with higher amplitude. So if you modulate saying, no, but this should have like a 2 or 5 times more importance than this one. So at the end, you're trying to fit more or less all the wavelengths and then fit in more or less all their heights. The theory is fine. In the paper, I use, I think it was 2 or 3 for calcium, more than the iron lines, and it worked well. Here I was doing tests and sometimes it worked, sometimes it didn't work. So be very careful with this one because can really just stop working or just have very, very bad fits. So just this is the way of creating the file. And then the important thing is, and this is really important. So if you run the code without any file called WHT as an extension, and with the first name, the same name that you use for the profiles. So in the control file, it's profiles.per. So if the code doesn't find any file called profiles n.wht, it will set the following. Sorry, it will set this. So the file containing weights does not exist. So then it will just run through it. But if you put this file, so a file with extension WHT and with the same name as the input profiles that you have, then it will use it always. So if you are doing test, just be aware that if you have it there, it will always use it. So if you don't want to use it, just move it to another folder. Okay. So for example, in this case, I have it here in this folder. That is where I was doing test. And here it's fine. But if I move this file to where I have the control file, then it will be included in the inversion, always. Okay. Okay. So just check it. You can write the values and then run the inversion and check the differences. But the important thing is that, so it's very simple to create. Just create another profile file with a different extension and then put values based on different wavelengths that will increase the impact those wavelengths has in the computation of the chi-square value. Okay. So we have now 2 weights between Stokes profiles and then wavelength dependent weights. Okay. So you can play with it. In my case, I think I was getting worse results. I think this was worse. Yeah, you can see that the line core was not very good. So you can play with them. If you're already getting good results, then just don't use them. But if you don't get good results, no matter how many nodes, how you play with the weights, then try to add it. Not too much. So, I mean, if you add like 10 on the line core of the calcium line, it don't fit the iron lines at all. But if you have like 2, then it is scaling the amplitude of the Stokes-B signals and linear polarization almost at the same level. So then it will fit both together. Okay. So just play with that. Okay. Any questions in this part? I think it went fast, but I really wrote everything. So if you check the script, you will see that it's very easy to follow. And the key thing is that if you run, just check if you see this message. If you don't see it, then the code is already taking into account the profiles, so the wavelength weights that you have in your folder. So if you see the message, it's not taken into account. If you don't see the message, it's including them in the inversion. Okay. Okay. So shall I go to tutorial 1C? Yeah. So it's new, so you can download it again from the Dropbox folder, and then together we are going to make it. make it work. Oh. So just let me know when you have it, and then we will go through it together. So the process is simple. I remove all the comments that we have in tutorial 1, and the only thing that we are going to do as a process is just create the atmosphere and then run the code and read the output. Okay, so what we are going to focus on is in the configuration files. But the process is we are going to prepare configuration files, and then with a given atmosphere, we run the code, we get the profiles, and we check how they look. Okay. So then to keep things easier, I already went to input, and in lines Non-LTE, I copy two new lines, 12 and 13. Okay, and I remove the last part because I want to do it together with you. Okay, but also I would like to just quickly cover how you can get this information, and from there how to get the energy levels that we need, and from there to get the transitions. Okay, so are you at this point? Is everyone here at this point? Yeah. Okay, so then sodium D1 and D2, they are important lines because they form higher than photospheric lines and a bit lower than a calcium, but they are relatively narrow compared to calcium, so they have high sensitivity to velocity, and also this stock signals, stock-based signals are relatively large compared to calcium signals, for example. Okay, so then the first thing is to go to the Solar Atlas. I usually use this web page. It's BAS 2000, and then you go to Solar Spectrum, and then you can play with the numbers that you get here. So I know already that it should be around this wavelength region. So this is 5,890 nanometers, sorry, Armstrong, and then I put a range of 20. And you can see that these are sodium D lines. When they were labeled, they use frequency. So then this is D1 and D2, even if in wavelength is increasing in this direction. Okay, so this is D2 and D1. Okay, so then you can just more or less get an idea of, okay, this one is 5,899, and then this one is around 5,895. Okay, then we go to NIST. So you go to Google, and if you type NIST space lines, you can get here. Okay, you try, yes, in Google NIST space lines, and then you will get this position. Are you there? Okay, so then now we are going to ask the NIST database of all the sodium transitions that fall between the range that we saw before. Okay, so we said between 5,880 something to 5,890 something. Okay, so in my case, this is 5,885 and then 5,896. Okay, and then you said retrieve data, and likely this is not iron, so you just get 2. Sometimes with iron, with just 5 Armstrong, you can get like 10 lines, but in this case, it's very easy. So you have 2 lines there. Can you try to do the same to see if you get these 2 transitions? Okay. So then the information you get, in general, you can also get the log GF, but now for simplicity, the important thing is wavelength. Okay, and then energy. The lower level has 0 energy because it's the ground level, and then there are two levels here. Okay. So if you are going to do the complete lines file, then we can check that these values match the ones that you get there. But for now, you can trust that this is correct. And the important thing is these two values. Okay. So then keep this tab open and just be aware of these two energy levels. Okay. So now for doing non-LTE computations, the next thing we did is an atom model, base of sodium, neutral one. Okay. So then again, for making things easier, I put an atom in the input folder called sodium 1 fine. Okay. So if we open the atom, we have, these are levels, energy, and these are transitions below. Okay. So then can you try just by yourself without telling me anything? If you can get which index we should take from here to include in the line list. So in the list, you have the energy levels that produce each transition. So now you need to look for those levels in this atom, check which index correspond to this level, to those levels in this atom, and then we go back to the lines list. I give you 1 minute and then I will repeat it again. So in the lines file for the calcium 8542 transition, we are telling the code that the levels that produce a transition in our atom are level 2 and level 4. So then we are going to compute the non-LTE populations of those levels to compute the departure coefficients there, and then to the inversion. Now we need to tell the code for the sodium lines, which levels in the sodium atom produce this transition and this transition. And for that, we need to know the energy of the levels that you get from here for each transition. And then you need to go the atom and look in your atom which levels have this energy. Look at here, and then put those values in the lines file. Is it easy to follow, or yeah? So who can tell me the values for the first transition for sodium D2? Who can tell me which index I need to put here? Zero, okay. Oh, sorry. 0 and 2. Okay, let's check. So 5889. 5889 is from 0. That's easy. This will be also 0 in the atom. And then here we have 16973. So then we go to the atom and we said, okay, is there a level with 16973? Yes. And it's 1. Okay. So then it should be 0, 1, 2. Sorry. Yeah, sorry. yes. It's 0, 2. Okay. So then we put here 0, 2. And now we are ready. Now, how about the next line? So this side was doing no with the head. So can you try now? 0, 1? Yes. Okay. Let's do it again. So if we go here, and it says 0 and then 16,956, then we go to the atom. In this case, it's easy because the ground level is always there. So it will be 0, the first one. And then 16,956 was the level. So then it's 1. Okay. So then this will be 0, 1. Okay. So we could also do this, but it will take some time. So for now, let's focus today on this some exercise that I hope is interesting and fun. And now with this information, if you got it right in your file, so just copy the same information. So then let's recap. We have that now our line list contains the correct atomic information and the correct non-LTE, let's say, information for running the code. Do you remember what is the next step to do the synthesis? Which file we need to change? We need to change 2, but which one you can say that we should change? Let's say in another word, do you remember that we can have a line, a list of lines inside of lines as long as we want? But how we tell the code that we want one line from this file? To which file? Wave grid. Okay, good. So then now we need to go to the wave grid and we open it and then we need to change it. We have 2 options now. They are close, not really close, but relatively close. So what do you prefer to do? Have them as a blend or in 2 separate transitions? Shall we put them as a blend? Okay, so then I need to put here, I will copy this line. And then which index should I put here? Can someone tell me? 12, 12 and? Okay, 12 and 13. Perfect. And then I will keep this like it is now. Okay. Although probably you can assume that we are not going to produce the lines well, so we will come back here. But let's do the synthesis. But before that, do you remember if there's an additional file that we need to change to compute those transitions in non-LTE? Atmos? Atmos? Yes, yes. So then we need to go to atoms, put input here. I already put the path to the local folder just to keep it simple, but we need to tell the code that this atom should be, like the calcium one, should be active. Okay. Okay, I will repeat. So you can have the transitions well defined in your line list. You can tell through the wave grid to the code that you want to synthesize a given set of transitions. But if you want to synthesize those transitions in non-LTE, you need to also set the specific atom as an active. Okay. Otherwise, it will synthesize the lines, but it will be in LTE. Okay. So I think we are ready. So let me see if I go back. So tutorial 1C. Okay, it's taking time because now we don't have only one simple atom like calcium. Now we have a sodium atom that is much more complex than the calcium one. So times will scale. and now it finishes. So let me go first for the time. So every time that you add an atom, it will increase the computational time. But if the atom is complex, if it has a lot of levels and a lot of transitions, it will be really, really increasing the time. It's what it is because we need it, but just be aware of that. Calcium is a really great line because, as we said, about sensitivity, formation height, but also because we can model it with a simple 5-level plus continuum atom. Okay. So then, what is happening here? Do you know what we are seeing here? What is in the left side? Or in the left side. What is this? Calcium. Okay. After that, 602 and 601, and after that, it's some line. It looks like sodium, but probably we are just not going enough to this side and also not to the other side. So if you see this when you are doing some tests, then just go back to the grid file and then let's say, okay, how about minus 5,000 and then 10,000. Compile again. Sorry. Okay, I went too far. Just 1 second. No, yeah, it's fine. I will do this and then I will repeat the error. I will reproduce the error. Okay, so then now it's taking time for computing. And then hopefully in just a few seconds. Okay, so now I think this looks much, much better, right? Now we have calcium, iron, and then sodium that is almost reaching continuum. And then this is D2, and this is D1. If we add in the line list the photospheric line that appear here, so remember that if you go to the atlas, there are some lines here. We can even also create this atlas. So it's just, we just need to add the lines information in the lines, the list of lines 5. Okay, but in principle you can add as many as you want. Photospheric lines, you just need to add the atomic information, and then chronospheric lines, or sorry, non-LTE lines, you need to add the index and the atom. Okay, so I will reproduce the error that I got now because I didn't get it before, but now I know what it is, and it's good to make it again. But until this point, are you following the process? So I will repeat it again. Imagine that someone says now, I want to do potassium. We have the atom ready. So then you should go to the atlas to check the wavelength more or less. Then go to the list, for example, and type the information for potassium between a given wavelength range. And then from there, you will get log EF, wavelength, the atomic information for the coupling, the LS coupling, so angular momentum, the spin, and everything. And then you go to your atom and you said, okay, which is the transition and which levels are the ones that I need to put. And then you put that in the line list. And then after that, you go to the grid file, you go to those lines, and then you provide a wavelength range that is enough for computing the spectral lines. And then you make sure that you are setting as active this new atom. I think I went fast, but it's fine. I think you will not you do this regularly, but I still just wanted to show you that in principle, decide and arrange, it allows to run any number of atoms that you want for any number of spectral lines that you want to have. You may run into convergence issues if the atmosphere is complicated, mainly if the atom is also complicated. But in general, there's no limitation in terms of how many atoms, how many lines you want to compute. Okay, so then just 1 second. So if you didn't notice, but when I put this 10, so the number was very large. So when I did this, it says error it appears something because it's the profile from the previous computation, but in fact, the code didn't run. And it's saying that we are using too many wavelength points for this transition. I think regarding Jonathan's question, I think is that. So we have 2000, but it's essentially per slot here. So the only entrance that it's using more than 2000 points, I think is this one. No. This is the combination of the three transition. I need to check. I'm trying to understand now. I realize that probably 2000 is here, the combination of the three. So for example, in this case, if you really want to do this with this sampling, then you need to go to the parameter file and then change KLD, for example, to 10,000. And then you just rerun and it will work. Okay. I will say it again. So right now, the total number of wavelength points that we can compute with design for the parameter, for the configuration that we have in the parameter file is 2000. But the code is telling us that with this configuration, it needs 2253. So it's not able to do it. So then you need to go to parameter in the source folder, change this value to like 3000, and then compile the code and then run again, and it will work. So it's one approach that we decided to follow, and is to keep things as low as possible, to keep it as fast as possible. And if someone wants to do it in a bit different way, you just need to change the parameter file. So it's flexible, but it's just that you need to change that based on your needs. And I think this is because for 1077 and they wanted to use memory as efficient as possible. And also when you run, it really goes faster the lower the numbers you have here. So I think no limitations so far with modern computers, but I don't really know how far. So, but probably if you put 10,000 here, I think it will be fine, unless it says that 10,000 there needs some value over there, but I think it will tell you. So you can adjust the parameter based on that. But I think usually it will print a message like this one. So now I'm concerned about Jonathan's question. I think it's how I feel, because now I've seen that this is the sum of this. But I think with nodes, hopefully it's not the sum, because 20 nodes is not so much for chromosphere, but I will check. If it's a total number, then I will ask to always put as a default something like 50, because then 50 is difficult to reach, because you need like to put like 10 in temperature, 10 in field, in minus side velocity, 10 in the magnetic field, something like that. But 20 is not so high, so I will check. Okay, so then in this case, if you just put 20, it will run. Okay, so then should I repeat again what we did, or more or less you got it? Okay, you have it now. So now the tutorial 1C that is in Dropbox is this one. So if you copy it again, or you already did it in your computer, it's working. So then you just can check it later and revise what you add and then add comments. But in principle, you can always download it. Okay, so I think we're going to take 10-minute break. And this is no. We already had it, right? Okay, so then how far to the next? Okay, so then I think it's better that I just talk a bit. You ask any question that you can have, and then we end. Okay. So then before questions, I will just to say two things. The first is that I think the SAR is very capable, but still we want to make it better. So for example, Daniela was asking me yesterday, I want to run calcium. And in fact, she was running it and was working, but the profile was not realistic because now design is only running under CRD. So remember, Han this morning was talking about a lot PRD. So the advantage of design and being able to always lean on our age is that we can do PRD as well. So we are already working on that, and hopefully by the end of the year, the code will be able to do PRD. For intensity, because it's mainly how RH works, but this means that if you're interested in inverting iris, magnesium 2, H and K data, you will do it in PRD. If you're interested, for example, in chromis, calcium 2, H and K data, you can do it in PRD, because those missions and instruments, they record all intensity. So then it's perfect for this configuration. So it will be CRD with polarimetry and PRD with intensity for any set of lines, for any set of atoms. Okay, we're working on that. I will keep you posted. And if you're interested, I will probably make some tutorial of how to do it, probably with magnesium data from iris, and then you can do it. Then Mateus is also trying to do something different. So he's working on off-limb observations, and he asked us, can I do inversions of, for example, calcium observations, but off-limb material like coronal rain or the effects? And we said, yes, but we need to change a bit the code, because the idea is that the code is now assuming line of sight component, but also is assuming that the radiation comes along the line of sight. But if you get above the limb, then the radiation is coming from below. So it's not the line of sight geometry. So then we're already working on that. So probably between the time that we get PRD ready, we will also allow the option of defining from where the radiation comes and then do the line of sight velocity inversions. So it will take time, hopefully not too much, but it's something that we already have on the list, because off-limb observations are also very important, mainly because there are things there that you don't see on disk. So this is also something that we are trying to do. The third thing, I think it's already doable, but we need to work on that. And the idea is, if you check observations from long ago, you will always get H alpha. Everyone is observing H alpha as a context, sometimes for analyzing. But if you look for inversions, non-LTE inversions of H alpha, it's not done in general. And as Han explained, I think yesterday, it's tricky to model the line, mainly because you need to model the lower level, that is Lyman lines. You don't usually observe Lyman lines because they are extreme UV. But we want to try to see if you have calcium and you add H alpha in the inversion, what happens? Because you cannot get crazy things because the calcium is going to constrain most of the parameters. But maybe H alpha can allow you to get a bit higher, or can allow to get better velocities. So then we are going to do that. We have the atom ready. So in principle, it's relatively easy. We have observations. For example, Nancy already has observation with calcium, H alpha, and iron. In principle, it's relatively easy to do it. What is not so straightforward is what we are going to get. So I think we will go from an inversion of iron and calcium, then we will add H alpha. And if this makes sense and we get an improvement, then we will definitely prepare a recipe for doing that, because most of the people somehow can get H alpha from a lot of sources, because we are always observing it. It's just that we don't do too much with it. Okay. I think these are the three main things that we are already thinking as a evolution of what we get now. And then in terms of me, I think for me, this is not the end of the workshop. I think it's the beginning of a collaboration. So if you want, get in touch with me. You're trying to do something don't spend 1 week trying to do it. Send me an email. Hey, why I'm not getting a profile with this configuration? And then I will quickly check and I will help. Okay. After that, when you become independent, it will be fine. But for now, I think I will really help you to go much faster if you just send me an email with the configuration files. I will check it and I will get back to you in maybe 1 week or something like that. And then you can continue. Because my approach is the code to make it open, to allow people to use it, to show you all the things that I know, but then let you run the code with your idea, with your preferences, and eventually get the results and analyze them in the way you want. I don't want to run the inversions for you. I want to allow you to do it independently, but always helping you to do it. Okay, so you have my mail. I usually are a bit busy, but still send me an email. And in a few days, maybe 1 week, you will always get an answer. Either share, either decide, or even arrange. You have hand, but also you can have me. And if you're trying to do synthesis with a given simulation or things like that, I can also help you to put it in the right format. So I'm available. Just busy, but available. So any project that you can have and that involve these two codes, just let me know and I will help you. Okay? Then questions. Yeah. Yes. Yes. So I will explain. I will explain what she's asking. So the idea is that by default, and I can explain you other day why is that we need uniform sampling for the spectral lines. So the spectral sampling should be uniform. In general, this is fine for a spectrograph and for all the synthesis that we are doing, but imaging instruments, they need to define specific wavelength points. And in general, they want to cover, for example, in the case of calcium line, they want to cover densely the core, like, I don't know, 5 or 10 points in the core. And then they said, I also want to have the wings, but as the wings, they are less sensitive to short scale variations. So I have like 1 point and then 2 points. So then the sampling between the wings and the cores is different. So then what we do there is we take the profile, we interpolate to a uniform wavelength grid, and then we tell the code that only the wavelength points from this uniform grid that correspond to the observation should be included in the computation on the chi-square value. The way we do it is that we just give -10 intensity to all the points that fall outside of the one we observe. Can be done in different ways, but the idea is that we make it uniform, just creating an interpolated vector that exactly match the wavelength points that you had. And then during the inversions, we tell the code, okay, compare the profiles, but the wavelength points that we didn't observe, don't take them into account. So it's just a trick for allowing the code running, but we only embed the wavelength points that we observe. It's the same process. Okay, more questions? You could ask. I'm leaving, so ask now because we will talk by mail or maybe even Zoom, but use the opportunity now. And if not, yeah, maybe. Okay, no, she's going to ask. Thank you. Thank you. She was going to ask, but thank you. It was for her.
So I'm sorry if I missed it, but what's the advantage of using multiple lines, like doing the inversion of multiple lines at the same time?
Yeah. So for example, let's think in the In this case, let's go back to tutorial 6. Let's think this case. Or, yeah, this one. So if you only observe the ion lines, the response functions that you see your left side are telling you that you are sensitive to the magnetic field only between log tau minus 0.5 and log tau minus 2.5 approximately. Beyond that, you don't see anything. If you only observe the calcium line, you are getting from there that you are sensitive, very sensitive to upper layers, but essentially lower layers, you don't see anything. So if you combine them, you observe them together and you combine them, then the code is combining essentially these two response functions. So then when it changes the atmospheric parameters, it's based on these response functions. And if it gets the fits well for the photospheric lines and the chromospheric lines, then in principle, you are getting the magnetic field from the lower layers to the upper layers well. So it's a way of getting better height coverage, and also adding more lines would mean in general better height resolution. Okay. So more questions? Yeah.
I just wanted to know how we can I mean understand how to use the number of nodes for the different parameters, like what we were doing with the tutorial 4.
Yes.
So I mean that is there any trick related to that? Because I mean we just wanted to get the accurate, I mean we wanted to be closer to the accurate results, but how should we know? Because currently you are telling us that what we have got through these profiles and else, but how we'll get to the accuracy?
Yes, yes, it's a good question. So as I said at the end, I want to share with you all the knowledge that I have, but I also, if you do something different, is fine, because in most of these cases, it's difficult to find a correct answer. But my approach is always the same. So two conditions I usually put. That temperature usually have a bit more nodes than the rest of the parameters, because it's the atmospheric parameters that most affect the others. Sorry, the SOX profile. So then, for example, if I go 2 nodes in temperature, I usually have 1 for velocity, 1 for magnetic field, but not the opposite. And for me, it's not usually normal to have 2 in temperature and 3 in velocity. That's, I think, not recommended, not advisable. So then a bit more nodes in temperature than in the rest of parameters. And then the second one, and this is my particular case, is as simple as possible. So if you get a good fit with 3 nodes in temperature, don't use 5. If you don't get it with 3, then use 5. If you don't get it with 5, then try to play either with weights or increase more nodes. But if you get it, and I mean reasonably good, with few nodes, then the better. So if you combine this, you will see that always, at least the first trial that I do is 2, 3, 5 in temperature, 1, 2, 3 magnetic field, 1, 2, 3 line of sight velocity, 1, 2 inclination, 1, 2, or 1 azimuth. And this is always my first trial. And after that, depending on the profiles and the results, I will start playing with other things. But in general, yes. Yes, yes, because temperature will dominate Stokes height, but also in the Stokes parameters and the Stokes polarization parameters. So it's the main one that will change everything. So it's better to get it more accurately. And also temperature always has a strange behavior because it goes from hot, decrease, temperature minimum, and then increases. But you don't need to have this stratification in general for the short optical depth range of formation for photospheric lines. So you don't expect that, for example, the velocity between log tau 0 and -1 goes from high, from velocity, then lower, then like this. But temperature always will do this complex behavior. So temperature, besides being very important for changing the parameters, is also the only parameter that since the beginning, it's always positive with variations, and then it gets hot in the upper part. Okay. Yeah.
I have a quick question about the sodium1_fine.atom file. So now I want to do that same thing, but for a new species. Where do I find the fine.atom file for that species?
Yes.
You have to build that from the NIST site.
Yes. So if you plan to do it for known solar transitions, you probably get somewhere an atom, mainly in the RH library. So for potassium, sodium, hydrogen, Balmer lines, Lyman lines, this is usually done. And for example, magnesium is starting to get tricky. We have done several atoms. And then if you move from there, then it gets tricky in the sense that you need to ask someone to help you creating the atom, or ask someone if they are already working on that, because there's so many people creating atoms, and it's really complex to make them, not because of finding levels and transition between the levels. This is relatively straightforward, but this will mean a huge atom that it's going to be hard to write, but you have the information. But the problem is that if you go this way, then your atom is so large that it will take like a few days to do one synthesis. So then the tricky part is that some people know how to start removing transitions, start removing levels, or start creating equivalent levels that will have more or less the same results, but simplifying the number of levels and number of transition. But this is really an art. And not many people are able to do that. So I think this is the main problem. So it can be done. There's no physical problem doing it, but it's tricky. So I think some people have worked on that, and you can check with them. But the main issue is that if it's not ready, then it will take time or a lot of effort to make it. But fortunately, magnesium HNK, Lyman, Balmer lines, calcium, sodium, potassium, magnesium 1, we have several options. So all of them are covered. Helium, helium is another, but it's in principle, we can do it. And in general, most of the lines that we are used to observe, we have atom models. So that part is more or less covered. But if you want to do iron in non-LTE, because you want to do a test, then you need to talk to someone to see if they have an atom or to start creating one. And it takes a lot of time. And do you want to add something there? Yes. Yeah. Yes. Yep. Yes. So I would say that right now, people that I know that can make the atom probably 3, 4. So, and they are relatively old. So be in a hurry if you are thinking of it. Because I spent some time with Han, and I think I can do it. You do it? You can do it, Ivan? Oh.
Because we outside of our field.
Yes.
Created all these models.
Yeah.
So this calcium, magnesium.
Yeah. Yeah.
But there are physics
Yeah.
libraries and things like that. That's all. They don't want to.
Yep. Yep.
And the judgment to your.
Yes. 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 So I said people that from all the people that I know, 3, but as Ivan said, maybe. Yeah, it's Han, Mats, Natasha, and I think that's all. Mats Carlson, yeah, and Natasha Shukina, and Han. And then probably students of Natasha like Andri probably can do it. And then students from Mats, maybe. And then I try to learn from Han, but I think I can do it. But the part that he says sensible, I think I'm not so good. But I think more or less the basics and where you can get levels and collisions and other things, I think I got it. So maybe I can try. Okay. Nancy, yes. 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 Yes, yes. So the chi-square that you see in the desire file and also in the SER file, I don't exactly know how to compute it. It's part of the upcoming tutorial, but I need to sit down with Vasily. I know that it's a combination of the difference between Stokes profiles, weighted with the signal to noise ratio that you provide in the control file, weighted with the number of nodes, and then I think another element, but I cannot do it by hand. This is the standard idea, but then you have several values, and I think it's because Basilio is adding weights related with some parameter in one of them, so I don't exactly know how to compute them, the three values. Can we put a normal one that people will understand that goes from 0 to 1, where with 1 perfect and 0 wrong? And he said yes, but I need to sit down with him to do it. So eventually, in the chi-square output values, you will have or a fourth column, or maybe just a third one, removing one of the others, that will go to 0, from 0 to 1. And this one, I'm asking him to make it independent of the inversion configuration. So just the difference between IQ, U, and V divided by the signal to noise, probably. I think this is what he's going to do. So then if you do one configuration, another configuration, and another configuration, you can compare. And the best value between the three is the one that you can assume as the best value. Right now, it will not work, because right now it's weighted with the nodes. So then if you change nodes or the weights of the Stokes profiles, then it will change. So then right now it's dependent on the configuration. And it's a chi-square that I think Vasily is using it internally for both SER and decide, and probably it has a meaning to do it in this way. But I have started writing the notes, and I want to sit with him to completely reproduce the value from an output profile and get the value that he gets there, and it will be a tutorial. But I haven't done it yet, so I will do it soon. So this is the first part. I don't understand the values, but if you get lower values for the same configuration, if you're using different atmospheres, the best value, the lowest value is the best. This is the first condition. Then we will have one that we can understand soon, and it will go probably from 0 to 1. So this is design. And then in the parallel wrap, when we run the inversion, we can use the threshold to tell the code, I want to do more inversions, I want to use all the initial atmospheres or not. And this threshold goes from 0 to 1. But this is computed by the Python wrap. So the Python wrap takes the output profile, it reads, it compares the input with the output, only intensity, and then takes, I think it computes the inverse of that, and then 1 will be perfect and 0 will be wrong. So this was implemented by Ricardo. And then the next step is, with Basilio, get the chi-square with 1 as perfect for the four Stokes parameters, but without including the configuration. When we get that, this will be the value that we will use as a threshold in the Python wrap. But so far, we have been evolving in different ways, and then sometimes everything is not completely consistent, but it's essentially that. The chi-square that Basilio is computing, it makes sense for the code, but it's not it makes sense for humans. So we will change that. And then we will make that compatible with the chi-square that we are using in the Python wrap that is computed externally by the Python wrap. Okay. Okay. More questions? No? No? Yeah. Yes. Yes, it's an option that was added, and I don't remember how was done, but in principle, it was included, I think, a few months ago, and I haven't tested yet. But in principle, yes. But I have done tests in the past with other codes, and it's really tricky to make it work because depending on the atmosphere, the formation will shift. So if you are fixing the wave, the optical depth where you want to have the nodes, you can just have your line formation shifted and they are not there. So we add it because we know that people will like to have it, and it's in principle it's working. Or this is the last I had from Basilio, but I haven't tested. So if you send me an email, I will try to sit down with him to just compute some test, and then I can show it to you, or just prepare a tutorial so then people can see it. But just remind me, because it's working. He told me it was implemented. So I think just as a context, he's asking, because right now we are using a specific number of optical depth points because we are saying that the nodes will be always located equidistantly in the atmosphere. Okay, so if you have two, will be the streamer, three will be one in the middle and two in the top, bottom, and top boundaries, and then four, so on. So then he's asking, can we decide where we point with the nodes? So imagine that I want to have three nodes, one in log tau -4, one in log tau -5, one in log tau -6, and then a fourth node in log tau -2. Because I know the calcium line is sensitive here, and the photospheric lines are sensitive here. So can I do that? The answer is yes, and definitely we should try it. But as I was saying, the concept makes sense, but it's the same as with the wavelength dependent weights. When you try it, it usually doesn't work as well. But definitely we should try, and it's possible now. Okay. More questions? No? You sure? Okay, so then thanks a lot. I think it was very fun, and I think it was a very good group. So I really enjoyed it. Thank you.
I just have a quick announcement. Well, two things. On the Spectropolarimetry School website, there is a section for inversion codes. I have added the Evans tutorial materials are linked from there. And more than the tutorials, which he may still be working on, there is also a link to the data that you might want to download, and that may take a little while. This is nothing in terms of volume, so at your leisure, just download it. I don't think you'll use it tomorrow, right? Even it's going to be the next day, but so that you know it's already there. And also below that, I have added the tar file for the magnetic field disambiguation code that Graham will be using on Friday. And he decided this week that maybe you guys want to try to install it and work along with him or not. The lecture on Friday, magnetic field disambiguation, is only a couple hours. He will work through a Jupyter notebook. He will run the disambiguation code online. You guys can try to install it if you want to. What you do need to install this code is the Intel Fortran compiler. So you can't do it with GFortran. So you might need to, procure the Intel compiler and try to install it. And he said he would be available through Discord.
Intel compiler is out. You need to pay for license?
No, you can get it for free if you're a researcher. You can say, "Oh, I'm a research. I work at the edu domain and get it." I'm downloaded it before, no problem.
But when? Because this stopped a few years ago.
I don't know.
So-
Probably a few years ago.
So check it because I did it that, but I think like 4 years ago they stopped offering this option. So only students they are allowed, but in principle. The Intel compiler? Okay, so then now it's free. And
I don't know. I've always done
okay,
it.
double check it because I paid for a license in 2018 because they stopped offering this option, and then I moved to G4gen because
And the reason you need this one is because it uses the MLK libraries from the Intel compiler. So feel free to try it. Graham will be really happy to answer questions if you do try it and run into issues. I'm going to share with him the Discord again and make sure he's sort of on it. But I encourage you to do it. I know it's late in the game, but if you do have time and you want to follow along with him, then install it. I think that's all.
Just double check because I'm really worried. But this was in Linux, right? Okay. So please, those with Mac, double check it because my impression is that Intel requires like $1,000 license. So so if you get it with Mac, just let me know because I sometimes want to check between the compilation with G4 and Intel. So if you get it run in your Mac by free, legally, just let me know because I was thinking that it was not possible. So
I know for a fact that Graham uses Linux.
okay, yeah.